Good morning, Gökhan.
Good morning. We were worried that you were missing, so.
You want to try sharing your screen, Vjaytala?
You just reached 30.
Shall I share my screen, Gökhan?
Yeah, John is sharing actually. Yeah, please go ahead.
Okay. Can you see my screen?
Yes.
Okay, great. Let me know when we're ready to start.
John, maybe we should go ahead and start. We have about 37 right now. So.
Yeah, that's that sounds good to me. So, Vjaytala, I'll give you a warning when you have 2 minutes left. Okay.
Okay.
And we're going to start with Vjaytala Mehra on development of GFS SFS models. Take it away.
All right. Good morning, everyone. My name is Vjaytala Mehra, and I work at NCEP EMC. And today I'll be talking about development of fully coupled UFS-based sub-seasonal to seasonal prototypes. These are in preparation for our next operational targets of GFS, version 17, GEFS, version 13, as well as SFS, version 1, which would be the replacement for our current CFS v2. There are a lot of people at NCEP EMC involved in this effort with me, and some of the principles are listed here. It's a big effort involving a lot of people. Also, we have additional community contributors, UFS being a community effort. So within NCEP, there are others, both within EMC as well as CPC, who are working with us. We have folks at Israel listed here who are equally working hard and conducting experiments with us. We have folks at GFDL who are also involved, especially on the ocean and waves components, as well as sea ice. UCAR and NCAR folks have joined hands with us, especially on the infrastructure side. They're contributing their ESMF expertise, and as part of the NOAA NCAR MOA, working on common infrastructure components of UFS, and of course, folks at NESI who are the resident ESMF experts and give us a hand when needed to help us move along. Here's a brief overview of some of the things I'm going to talk about today. So starting with the motivation as to why we are doing this. Talk briefly about all the current UFS-based coupled systems which are under development. Then focus on the coupled UFS S2S model configuration. Talk about how we are conducting our prototypes and discuss some results. And I'm going to end by talking about some of our near-term future plans. So in context of motivation, the Weather Service issues global forecasts at primarily 2 timescales. Weather or medium range, which would which would come from systems like GFS and GEFS, and as well as seasonal from CFS version 2. The Weather Act, around 2 to 3 years ago, from Congress instructed us to provide forecast guidance from weather to subseasonal and seasonal scales. So I formed our role here. Meanwhile, the Weather Service is in the process of upgrading its operational modeling suite using a new atmospheric dicore, which is FE3, developed at GFDL. And we are using this opportunity to upgrade and unify all our modeling capability across different timescales as we move our operational suite to use the new dicore. In terms of the strategic vision we have as we conduct these upgrades and bring in new systems is to simplify our current production suite, which is shown in the schematic on the left. So as you can see, it's quite a quilt of different operational systems which are connected to each other. And what we want to do is to go from the schematic on the left to a schematic on the right, whereby the quilt of models and products we have, which have been created over the last few decades, actually, to implement solutions rather than addressing all the requirements we have as part of our mandate here at the Weather Service at NCEP. And we move to a product-based system that covers all the existing elements of the modeling suite, and but does so in a much more systematic and efficient and a modular manner, which makes it easier for us to maintain the production suite and conduct efficient upgrades. So let's talk a little bit about the UFS, or the Unified Forecast System. The schematic is shown on the right, but it consists of the following components. These are all community developed components. So we're using NEMS for infrastructure, or NOAA's environmental modeling system. We have adopted CMEPS as a mediator. CMEPS, which stands for Community Mediator for Earth Prediction Systems. It comes to us as part of the NOAA NCAR MOA. FE3 dicore, and we have using that with a CCPP physics driver, or the Common Community Physics Package. We have MOM6 ocean model for S2S. For now, we have HICOM ocean model for weather scales. Wave component is from WaveWatch 3. Sea-ice is size 6. We've chosen NOAA-NP as our land surface model, and we'll be using GoCart for aerosols. So each component listed here has its own authoritative repository. Most of them are public on GitHub. And the NEMS infrastructure allows us to connect specific versions or instantiations of these repositories together to create a coupled system. And more details on our approach in building the UFS is at the ufscommunity.org hyperlink. So we have quite a few coupled developments taking place within the UFS framework and using the UFS paradigm. Each one of these is a work in progress. And it's actively being tested as listed here. And today, though, I'm going to focus on the one at the bottom right, which is circled in red, which is the 4-way FE3 GFS MOM6 size 6 WaveWatch 3 global coupled system, which has been developed to address S2S scales, roughly with 25-kilometer atmosphere, quarter degree ocean and ice, and half-degree waves. And in the next talk, Vjaytala Pragata would actually be focusing more on the UFS paradigm and infrastructure and talking about all these developments. So we call it the UFS weather model, though it is focused on weather as well as S2S scales. For atmosphere, as I mentioned, we have Fe3 dicore. We're using GFS physics with GFDL microphysics. CCPP physics driver. We're using C384, which is roughly 25 kilometers with 127 levels. Ocean MOM6. Quarter degree tripolar grid, 75 hybrid levels. It is the OM4 setup as described by Atcroft et al. Back in 2019. Waves, WaveWatch 3, half degree regular lat long grid with ST4 physics, as described by Arduin et al. 2010. For ice, we recently switched to size 6, which comes from Los Alamos. It's part of the CIS consortium. Quarter degree, it's using the same grid as the ocean, and we're using 5 thickness categories. The driver is NEMS, and the mediator is CMAPS. So there's a kind of a high-level schematic on how things are coupled using CMAPS and within NEMS framework, the 4 main components. So here the atmosphere ice fluxes are primarily computed by the sea ice model. The atmosphere ocean fluxes are computed within the atmosphere model. The wave model sends roughness length information to the atmosphere, and it also sends Stokes drift to oceans to describe sea state dependent Langmuir mixing. So as I mentioned, we have been conducting prototypes, and we've completed 6 of them so far. Each one of them using specific initial conditions as shown here in the table. And we switched from size 5 after prototype 4 to size 6 with 5, and also switched from our legacy NEMS mediator to CMAPS. And with prototype 6, for the first time, we introduced a fractional grid to address the accuracy of flux computation, especially near the coastlines. So far for all these 6 prototypes, physics settings have been mostly kept unchanged. We changed some things with prototype 6, but mostly made sure that we are addressing all the bug fixes. And our plan is to conduct tuning when the building or the engineering phase of these prototypes of the coupled system is completed. So here's a summary of the main features. So prototype 1 was our first 3-way coupled system using Fe3, MOM6, and size 5. With prototype 2, we got better updated ocean initial conditions from CPC. And we changed the coupling strategy, introduced a slow fast coupling time steps. Prototype 3 or 3.1, we got better sea ice conditions from CPC, introduced river runoff, and changed how we were calculating the fluxes between the sea ice and the ocean models. Prototype 4, we introduced CCPP physics driver and added WaveWatch and WaveWatch coupling, wave coupling to the system, making it a 4-way coupled system. Prototype 5 introduced CMAPS mediator, swapped out size 5 with size 6, and also had a few updates for wave atmosphere coupling. And with prototype 6, we introduced fractional grid and doubled our vertical resolution from 64 levels to 127 levels, and also updated some of our physics. So in terms of physics updates, we essentially adopted the GFS version 16 physics with prototype 6. The GFS version 16 was made operational in March of this year. So as I mentioned, vertical resolution was doubled from 64 to 127. For our PBL, KEDMF was replaced with a scale-aware TKE EDMF scheme. I also revised our background diffusivity. For gravity wave drag, we introduced parameterization for subgrid scale, non-stationary gravity wave drag. Some radiation changes, including calculation of solar radiation, accounting for water clouds, and as well as change some of the assumptions on cloud overlap representation. For microphysics, GFDL microphysics scheme was updated to account for computing ice cloud effective radii. And for our land surface model with prototype 6, we're still using NOAA. Couple of updates on ground heat flux calculation over snow-covered surfaces, and changed how we were accounting for vegetation impact on surface energy budgets, especially near urban areas. Next, I'd like to go over some of the evaluations we have been doing. So here's the test plan which we have followed for all our prototypes. So we initialize the system on the 1st and 15th of each month and conduct 35-day run forecasts for each setup. And we're repeating this over a 7-year time period from 2011-12 to 2017-18. We chose this period because it covers important El Nino and La Nina years, as well as years of very low sea ice in the Arctic. This gives us a pretty large sample, or large enough, I should say, sample, to calculate some statistically relevant metrics so that we can assess our progress or lack thereof. And the model components are still being initialized independently. So the overall strategy is conduct these discrete prototypes when we add new things or new components with fixed benchmark settings and metrics. And then we evaluate the results for spatially and temporally persistent patterns for both system biases, as well as calculate our skill scores. So here we're looking at the impact of changing or introducing better ocean initial conditions. This happened when we moved from prototype 1 to prototype 2. We're looking at anomaly correlations of SST in the Nino 3.4 region. And as you can see, as we move from prototype 1, which is in orange, to prototype 2, which is green, we saw good improvements in the AC scores. As compared, we improved all through weeks 3 and 4, and improved upon the skill coming from CFS. Similarly, when we moved from prototype 2 to prototype 3.1, we got better sea ice initial conditions, and we saw improvements in how we were growing or melting sea ice. So prototype 3 with the better sea ice initial conditions did better as compared to earlier prototypes, as well as CFS. And since then, the progress we made with prototype 3 has been sustained in our follow-on prototypes, as shown in the figure on the right, which is looking at threat scores for the Arctic, defined as for those points with ice concentration of greater than 0.15. But there are some problems too. So here's looking at SST biases compared to Ostia in the tropical regions. And we see a warm bias of roughly 0.5 degrees Celsius, starting with prototype 1, but this bias is still there through prototype 6, and it tends to grow as we move from first few days, first week of the simulation to week 3 and 4. But on some other parameters, we made some improvements. So this is looking at the OLR bias as compared with the high-resolution infrared sounded data. And we found a lot of positive bias with prototype 1. But as we moved forward with our prototypes, and especially with prototype 6, we see that we have the system has reduced the positive bias quite a bit. And okay, all right. Similarly, here are the anomaly correlation scores for tropical SST and CONUS 2-meter temperatures and precipitation. As expected, the correlations are higher for week 1, and the correlations go down as we move for the greater lead times. And here is a kind of a summary for weeks 3 and 4, anomaly correlation scale, comparing all prototypes with CFS. And in general, we see a boost of SST scale from prototype 2 onwards, which can be attributed to better initial ocean conditions. For 500 millibar anomaly in the northern hemisphere and CONUS T2 2-meter temperatures, scale is varied between 10 and 20%. CONUS precipitation scale remains low. Some improvement with prototype 6, but remainder of ACs have quite similar across all the prototypes. MGO indices, very quickly, this is looking at RMM1, RMM2 MGO indices with prototype 4, 5, and 6. Some improvement or some degradation with prototype 6 with RMM1, some improvement with RMM2, and neutral when you look at them together. Also looking at the MGO amplitude and phase errors, we find that positive MGO amplitude bias in all prototypes, and slower MGO bias and also in all prototypes. Some differences in how they treat, the other prototypes are treating weak and strong MGO events. So in summary, prototypes gave us, once upgraded with better initial conditions for ocean and sea ice, improved the forecast for those fields. And the benefits have been sustained in subsequent prototypes. Most of our scores, global as well as CONUS in weeks 3 and 4, are consistently above those of the operational CFS. The spatial and temporal structure of our biases and skill scores is generally similar across all the prototypes. This gives us confidence that the system is fairly robust from an engineering standpoint. And the bias reduction and skill improvement are improvement from inclusion once we have our own DA, and we conduct a physics tuning, which is the plan for future prototypes. And this is the last slide showing we've completed prototype 6 and our plans for prototype 7 and 8, which include bringing in NOINP, land surface model, go-kart for aerosols. We plan some major physics upgrades for radiation, microphysics, as well as convection, and some minor physics updates also for PBL and surface layer, and exploring marine DA. That's all I had. Thank you.
Great. Thank you, Avichal. Do we have any questions for Avichal? Hey, so my question would be, how do you plan to address that warm bias in the latest configurations?
So
it's associated with precipitation with the ITCZ.
yes. As shown here on the slide, Gokhan, we are considering quite a few physics upgrades for the atmosphere component, and assessing the impact of those upgrades, and looking at specifically at the biases which you have seen already, whether it's for precipitation scores or for the SST biases, as I discussed, and hope to make progress. Once we have all these physics schemes in there, we plan to then conduct kind of a tuning of the overall system and look at all other components and come up with configurations or options which reduce those system biases.
We have a question from Isla Simpson. I'm interested in the change you mentioned to the representation of the ground heat flux over snow-covered surfaces. Do you have any more details on what that change is and its effects?
Yes, perhaps I'm not the best person to address that question, but please write to me and I will put you in touch with the people who looked at that in great detail and give you more information on what that change was and how it impacted the results.
Okay, Vjaytala, she says, sounds good, thanks. So let's move on to Vjaytala Pragata's presentation. Oh, there you are, Vijay. Nice to see you.
Nice to see you, John. Good morning, everybody. Let me try to share my screen.
You should be able to share now, Vijay.
Yeah, I got it. Can you see my screen now?
That looked good.
Yes.
Okay. Thanks, Avichal, for setting the stage. I'm supposed to go first, but definitely you going first helps me continue piling on the UFS development. And my focus will be mostly on the R2O project, the research to operations project that was launched last year as a collaborative effort between OAR and Weather Service, joining hands along with the community. So the talk mostly will be focusing on this project that we have already reached about a 1 year of development in this process. So the outline for my talk, I will start with some recent UFS applications that transitioned into operations, focusing on the GEFS V12, which is the Ensemble system and is the first ever subseasonal application in operations. And this is based on the UFS coupled model, where the wave model and the aerosol component are coupled to the atmospheric system. Likewise, we just recently implemented the GFS version 16. It is an upgrade to the original FE3-based global model that was implemented in 2019. So this is a major upgrade to the medium-range weather application, where we not only extended the vertical levels and the model top, but also coupled it to the wave model. And then I'll shift my focus to the R2O project, along with the coupled model development for future global model implementations for both medium-range, subseasonal, and seasonal forecast applications. Just to revisit what happened last year in terms of implementing the global Ensemble forecast system. This is a major achievement or accomplishment in terms of expanding our capabilities of the Ensemble system from medium range to subseasonal scales out to 1 month, to be precise, 35 days. This is using the FE3, the finite volume cube sphere version of the dynamic code that was used in the GFS, along with the physics that was used in the GFS operational model at the time. We updated the model uncertainty by introducing the SPPT, the stochastic physical perturbation tendencies, and also the SCAB, the stochastic kinetic energy backscatter. The SSTs are treated in 2 different ways. One is the NSST, that near surface sea temperature, and a 2-tiered SST where we relax the forecasted SSTs to CFS predicted SSTs. This model has been increased in resolution from about 35 kilometers to 25 kilometers and extended the forecast length from 16 days to 35 days to support subseasonal weather application. The Ensemble members also increased from 21 to 31, and the resolution of the output is made available at 1/4 degree, 3 hourly for the first 10 days and 6 hourly for the rest of the 35 days. The advantage of this system is that it also came with a 30-year reforecast and a 20-year reanalysis that was done separately from this model implementation. Just to give you more details in terms of the waves and aerosols, we have one-way coupling to global wave system, only provides 16-day forecasts. And aerosols, this is only one member, deterministic member that's coupled to the atmospheric model, goes out to 5 days only and 4 cycles per day. This got implemented in operations on September 23rd. The reanalysis and reforecast was done prior to the implementation. We have a 20-year reanalysis going from 2000 to 2019. This was led by Astral Physical Sciences Lab, and a 31-year reforecast from 89 to 2019. This was led by EMC. As you can see, we have 11 members every week going out to 35 days, and 5 members every day going out to 16 days. And this data is available on Amazon Web Services for the community to have access, easy access, and a lot of interesting research is going on using this modern reanalysis and reforecast data. Some outcomes from the evaluation of this long-term data. This is an evaluation that was done by CPC comparing the GAPS-V12 subseasonal experiment, that SUBX, and the CFS. And the plots that we are showing here are the anomaly correlations for week 2 in the top panels, and the weeks 3 and 4 in the bottom 2 panels. And you can see easily that the GAPS-V12 has much superior skill in both of these time horizons in the Northern Hemisphere as well as the Pacific North American region. Especially in the PNA region, the improvements are rather more impressive than in the Northern Hemisphere. MGO, it's another metric that we, for the first time, can evaluate from our GAPS-V12. This is comparing with the CFS version 2. The FE3-based GAPS-V12 has increased the MGO skill by about 2 days. This improvement is also seen in all MGO components like the 200 millibar, 850 millibar journal winds and the OLR. This is definitely an improvement compared to the CFS. We also looked at the comparison with SUBX. This is only for a small period like 2000 to 2016. Here also we can see the FE3-based GAPS-V12 has an advantage of about 2 days compared to the SUBX. Similar improvements are shown for the MGO components. We also looked at the performance of GAPS-V12 by decade, and I think we found that the 2000 to 2018 has the highest skill, followed by the other 2 decades. There are interesting features here in terms of how we can evaluate the MGO, either using the CFSR climatology or the reanalysis climatology. And this is another active area of research that I would say that will help understand the behavior of the subseasonal prediction skills from our Ensemble system. The propagation of MGO, this is a topic that we all know CFS suffers a lot in terms of demonstrating the accurate propagation of MGO. This shows that the OLR anomalies compared against the GAPS-V12 and the CFS is that the spatial correlations are well captured in the period of the 30-year period that we have analyzed here. The correlation is pretty much matched with the observed anomalies. Very good eastward propagation of the signal of MGO in the Eastern Indian Ocean. However, it's a challenge that we cannot capture the northward propagation or the amplitude of MGO accurately. So that's something we expect that the fully coupled models will be able to address. The other important metrics that we monitor for subseasonal forecasts are the cornice temperatures and precipitation. The FE3-based GAPS-V12 subseasonal forecasts have shown rather impressive improvements, even with the raw ensemble forecasts. The RPSS has shown much better scores compared to other SUBX models that were used by CPC. Similar analysis is done using ERA5 as an independent reference. We computed the biases of the 2-meter temperature The top two rows are the top two plots are for the sub-X, land only Northern Hemisphere and North American region. There is a strong positive bias that was shown in the 2-meter temperatures, especially in the weeks 3 and week 4. And that bias has been substantially reduced with GAPS V12. The summertime warm bias definitely has improved from the reforecast data that we produced. Similar advancements are happening because we share the same atmospheric model between the GAPS, the subseasonal system, as well as the medium range weather application. This is important that we make cautious advancements to both the systems that cater to all global applications. As Avichal described, the P6 is actually using the latest GFS version 16 configuration. And the major goal for all our applications here are to address the known issues while attempt to improve the forecast skill. So we noted excessive cold bias in the winter season, the progressive bias for the synoptic scale systems, less skillful DC track forecasts, especially for the stronger storms, and also biases in the stratospheric temperature and precipitation dry biases. So these are documented while evaluating the GFS version 15. We made several changes to the science, both the resolution as well as the physics and data assimilation. And all these changes helped mitigate and reduce those biases that were noted earlier. And for the first time, the global model now absorbs the global wave model as well, which is not only to provide better forcing for the wave models from the atmospheric system, but also to reduce the complexity of the production suite and simplify applications and operations. Data assimilation is another area of research that we continuously make advancements with. We replaced our ENKF with LETKF and also introduced the 4-dimensional IAU, the incremental analysis update, to better assimilate the time variant data sets. We also have several new data sets that are coming in. This is still focused on the atmospheric system. I have news on the coupled data assimilation later on that I will describe. So using this as a backdrop, the UFS R2O project was kicked off last July, which is now a community-based model development for the coupled models as well as all UFS applications. And this project is led by 3 individuals representing 3 parts of the community. Jim Kinter from George Mason, representing the research community outside of NOAA, myself representing NWS operations, and Jeff Whitaker from SRL PSL, representing the NOAA research. And this is a $15 million project that was funded collaboratively by OAR and the service. And it's about 120 people working in this project, supported by this project. And you can see the collaborations range between NOAA labs as well as NCAR, universities, and Navy. And these collaborations are expanding as we speak. So it has a 2-year outcome that was specified. Originally, it was meant for developing a 5-year plan with a 2-year outcomes well defined. The target is to develop the global systems, the GFS version 17 and the GAPS version 13, and also focus on the regional high resolution aspects for the short range weather, which are the RRFS, the Rapid Refresh Forecast System, and also the Hurricane Analysis and Forecast System. The outcome clearly articulates the need for developing a fully coupled land, ocean, sea ice, atmosphere, aerosol, global ensemble prediction system, including coupled data assimilation, along with other convection allowing ensemble systems, and also sunset existing global models and mesoscale prediction systems that can be replaced with the UFS-based applications. The 5-year vision, which we are pushing towards, is to advance the coupled data assimilation capabilities, allowing observations of any component to update all components, advanced hybrid and 4D-UR algorithms for data assimilation, enhanced use of satellite radiances. And there is a new effort that was initiated by Joint Center for satellite data assimilation called the JEDI, which is a joint effort for data assimilation integration for all forecast systems. And on the physics side, the next generation moist physics, unified from the convection allowing scales to global scales, inline air quality prediction for direct aerosol feedback, and other enhancements for high resolution applications. And we also expand the scope of UFS to include coastal inundation, storm surge, surface hydrology, space weather, and also broaden the partnership both inside and outside of NOAA. The structure of this project is well laid out here. There are three application teams: the medium range and subseasonal to seasonal prediction led by Christiana Stan and Franklin Yang. Short range weather, Curtis Alexander and Jacob Carley. We have cross-cutting infrastructure supported by leadership from Rocky Dunlap and Tara Jensen. We have sub-projects clearly identifying various components that are being developed in a collaborative way. And all these components are being supported by the cross-cutting infrastructure. And we're going to have a first annual meeting in a couple of weeks to demonstrate the progress that was made so far. You already heard from Avichal about the UFS weather model. There are multiple components that are already built into the UFS weather model, all the component models, as well as the software infrastructure that combines all these components in a nicely well-articulated fashion. The weather model is already supporting multiple applications that are currently being developed. And we are looking into advancing our capabilities using this collaborative shared infrastructure. And what you saw from Avichal's presentation is that we have the S2S scales, quarter-degree atmosphere, quarter-degree ocean, half-degree waves with an FE3 GFS, MOM6, I6, WaveWatch 3 that's being actively developed and tested. And I wanted to focus on some contributions from the community in evaluating our coupled model prototypes. This came from George Mason, and they looked at the RMS errors for the ENSO mode and intraseasonal oscillations mode. And you can see there are two prototypes described here, the prototype 2, the earlier version of the coupled model, and P5, the more recent or slightly relatively recent prototype. You can see the error structures of the RMS errors. For instance, here it's 850 hectopascal meridional wind. The southwest northeast orientation of these errors have changed into north-south orientation. In the intraseasonal oscillation mode, the opposite signal is seen. We need to understand why or what the relevance of these RMS error structures are. Similarly, there are differences in capturing the extreme values. The P5 was shown to be degrading the values of 95th percentile, both for 2-meter temperature and precipitation. And that's something that we continuously evaluate and seek support from the community to understand and diagnose these issues. Moving on to impact of the new stochastic physics. This is a cellular automation-based convection scheme. This has been extensively tested and shown that for MGO propagation, both amplitude and phase along with propagation is better captured with the cellular automata-based convection scheme. The GFS control is having no such stochastic perturbations for the physics. That shows a kind of a stagnated MGO, whereas the other schemes that we used here have accurately captured the propagation of MGO more nicely. This is something that the UFS R2O project has supported. We're also continuously looking into enhancing the representation of uncertainty in other component models. One is for the ocean model here, we are testing two different stochastic physics. One is the sea surface height spread, and the other one is the ocean SPPT perturbations. The quarter-degree model shows more variability in the western boundary currents and also in the southern ocean. And this will continuously be enhanced both for the coupled data assimilation as well as for forecast applications. Land stochastic physics is also another active area of development.
2 minutes left.
Perturbing key land surface models was the best method for accounting for land model uncertainty. We will hear more from Mike Barlage on this in this meeting. There is a new paper that's coming out to describe these methods very soon in the Journal of Hydrometeorology. Land atmosphere diagnosis is another area of importance here because it has significant impact on the subseasonal, seasonal climate predictions and the predictability. The ongoing work includes troubleshooting the energy and water budget closure, both in the NOAA-MP and the NOAA models offline, develop noise reduction corrections, setting up ability to assess coupled land atmosphere model behavior, and also targeting extremes where land is relatively more important. And all these tools are being developed to assess the model development activity to support the coupled model advancements. The new emphasis is on data assimilation. We have land data assimilation system that's developed as an offline capability. It's based on the JEDI, and it's still in progress, but once this is done, we will be able to develop more accurate land initial conditions and the forcing data that's coming from meteorological models from GFS and the GDAS. They definitely can take advantage of this new architecture to develop the land analysis system in the coupled model. The ocean analysis, we are actively working on 40-year reanalysis using next generation global ocean data assimilation system. This is also based on JEDI. The production is almost complete. This will help CPC to advance their monitoring tools, as well as provide a basis for future coupled model data assimilation systems to represent the SSTs and the ocean conditions. This system is going to have a 40-year reanalysis starting from 1979, and this data will also be made available to the public for research and development purposes. The coupled reanalysis development, the atmospheric model is now adding all these component models. The global innovation statistics are shown here using API's ocean coupled analysis system has shown rather nice response. And
can you hear me?
Yep.
Okay.
Yes. So this is going to be developed as well as tested using the cloud resources. Computing requirements are huge for this project, and we are trying to identify those resources to complete the 30-year reanalysis and reforecast using the coupled model for future global model application. So we are moving into a new WCOS for future operational implementations. This is going to be 3 times more powerful than what we have currently, a 12 petaflop machine. And we created a notional implementation plan that will call for a major implementation in 2024, where we combine both the GFS and the GEFS along with the data assimilation capabilities, and plan for the seasonal forecast, which is a replacement of CFS as we go into 2025-26 timeframe. So more details about the UFS and the R2O project are available from this website here, and I'll be glad to take any questions, and thanks for your attention and the opportunity.
All right, thanks very much, Vijay. We have time for a quick question before moving on. Any questions for Vijay? Okay, well, thanks again.
This is David Considine. Can you hear me?
Yes, we can hear you, David.
Oh, okay. I'm sorry. I'm on my phone because my audio on the computer wasn't working, so I'm not really quite sure how to mute and unmute myself. But anyway, I had a question for Vijay, kind of about the cellular automata. You know, you use a cellular automata approach for MGO propagation. You get a better representation, I guess, of the MGO, but I'm wondering about predictability. Do you think this is something that will improve the model's capability to predict the MJO? Is maybe that's a little too broad a question, but I'm wondering, you know, I haven't heard of the use of cellular automata before in parameterizations and Earth system parameterization, so I'm just kind of curious about it.
Yeah, that's a great question, Dave. The idea here is that the tropical convection that has a significant influence on MJO amplitude and propagation. You know, we have known issues within our GFS convection schemes that we are using, especially at longer lead times. And by introducing the cellular automata, we are trying to improve the representation of uncertainty and control the behavior of the convection. And that potentially has helped influence the MJO predictability in our deterministic system. We are going to test that in our ensemble systems to better capture the variability and also the predictability of these low frequency modes.
Can we get Clara Orb and Ron Miller? I'm not sure who's presenting first. All right, it looks like their presentation's right on. Well, thanks again, Vijay. Who are we starting with, Clara or
Hi, John. This is Ron Miller. Can you hear me?
Okay, yes, I can hear you.
Okay, great. Can you see the slides?
Yes.
Perfect. Okay, great. Let's see if I can see the slides.
So, are both of you speaking? Is there?
We are. So I'm gonna advance the slides. Sorry, let's pull up the. Okay, great. Okay, so this is basically examples of just the kind of predictability work we've been doing at NASA GIS with Model E. This is a collaboration with a large number of people. I'm going to talk about three, actually the first and the last topics, and Clara's going to come in the middle and speak about the QBO and teleconnections. Okay, so the first topic is seasonal predictions by analogs, and this is some work by Nathan Lenson and Gavin Schmidt, and they were basically inspired, motivated by some papers by Wei Ding that came out over the last couple of years. The basic theme was doing seasonal prediction by analogs, and the idea is if you have an observed state, you look in a library from a PI control, and you find the best possible analog you could find. And we and Nathan and Gavin have been using SST and SSH. And then the idea is that if you want to understand, or if you want to build a forecast for your observed state, you look in your analog library, you look in the PI control run, you find the best analog, and then you see how that evolved over the next 12 to 15 months. And then that essentially is your forecast. You do this not for a single analog, but in fact, you look for a number of analogs so that you can create an ensemble. I think Nathan in particular chose 15 ensemble members, so he chose the 15 best analog states. What he was trying to do was basically extend the analysis of Wei Ding and collaborators to the CMIC 6th generation of GIS models, E2.1G and E3G. He also looked at seasonality of forecast skill and dependence of the forecast skill upon the length of the analog library or PI control run. So this is one example of hindcast skill. So this is the anomaly correlation at a 6-month lead time from 1960 up to the present. And there is the correlation, the anomaly correlation skill over the tropical Indian Ocean and the Pacific for model E3 on the top and E2.1 in the middle. Just in the interest of time, I'm not going to go into really the differences between the models, but in general, this method seems to show the highest anomaly correlation skill at 6 months in regions of large SST variability, in particular those associated with ENSO. There's less skill over the tropical Pacific. It's possible that where SST variations are smaller, and it's possible that precipitation might lead to better forecasts, or hindcasts rather. So this is a plot essentially of anomaly correlation as a function of lead time on the vertical axis, and forecasted month on the horizontal axis. The top is model E3, the bottom is E2.1. High correlation, high model skill basically is associated with blue colors. And so what this shows is the classic spring predictability barrier. You can see that essentially your anomaly correlation skill drops off rather markedly for forecasts in the late spring, early summer. And as you go later in the year, you actually have the ability to make better forecasts for those months. And then it's actually in the early winter that the model has the highest forecast skill. One of the limitations of the anomaly correlation is that it does not reward a model for having a good forecasted amplitude of the pattern. It only is interested in the normalized pattern. So to incorporate amplitude effects, Nathan is looking at something called the mean squared error skill score, which includes amplitude effects. You can see for E3 on the top, the results are qualitatively the same. However, for E2.1 G, in fact, we have prominent amplitude errors that really degrade our forecasts, especially around the spring predictability barrier. And so I think what this means, in particular, the red colors show where this skill score is less than 0. This is a place where the forecast is less skillful than climatology. So Nathan has basically isolated the effect of the amplitude on the error skill score, and this is shown in the panels on the right, which shows the amplitude bias, and predictably it's relatively large for E2.1 in the spring and early summer months. This was not a surprise to us. We've known that the ENSO amplitude is unrealistically large in model E2.1G. It's about 20% too large, and so obviously that impacts the forecasts that we make using this model. Okay, so finally, Nathan addressed the question of how large of a PI control library do you need to make skillful forecasts using the analog method. This is basically a plot of the mean squared error skill score as a function of the number of years in the PI control library. And you can see that for basically PI control runs longer than about 200 years, that basically you're not getting much improvement by making the PI control run longer. Less than 200 years, though, at longer lead times like 6 or 9 months, there is a penalty for, or you do have more of a challenge in finding good analogs. So this suggests, at least for model E2.1G, it's best to really have at least 200 years of a PI control library from which to select analogs. So at this point, I'm gonna pass the mic to Clara, who will talk about the QBO and predictability.
Great, thanks, Ron. I hope you can hear me. So I'm going to switch gears just a little bit. Now I'm going to be talking about some work that we've been focused on using the high vertical resolution version of Model E. This model is called E2.2, and there are 3 references that are listed on this slide, which document the behavior of that model, both in historical pre-industrial control as well as in some future increased CO2 simulations as submitted to CMEP6. So I'm going to be talking about kind of a topic that Yaga touched upon in her talk yesterday, which is the potential for stratospheric variability to impact tropospheric teleconnections. And specifically, I'm going to be focusing on the quasi-biennial oscillation, which is shown in terms of the tropical zonal winds plotted in this figure from David Rind et al. In 2020. And the QBO in E2.2 is generated largely owing to the incorporation of non-orographic gravity wave drag, which is tethered directly to parameterized convective sources. And so the QBO in this model is the period is consistent with observations, and its peak-to-peak amplitude is also pretty good, albeit slightly underestimated, consistent with biases that we see exhibited in other stratosphere resolving models. So next slide, please. So I'm talking about this in the context of this workshop because previous studies have suggested that the phase of the QBO can modulate ENSO teleconnections to northern latitudes. And so these are 3 such references. And so as such, potentially this represents an important source of S-to-S predictability. But previous studies have been limited in a few respects. Either they've used observed SSTs, so perhaps they're not capturing some component of atmosphere-ocean coupling, which is important, or they've used a nudged QBO, so the QBO in effect can't directly respond or interactively to changes in SSTs and parameterized convection. Or, and this is probably the most relevant point, they've used single integrations, which are relatively short or smaller ensemble sizes. And so I'm just thinking about a comment that Isla made yesterday in response to one of the presentations. That comment being that, really when we're looking at the interaction between these modes of variability that often occur on timescales of 2 to 3 years or still longer, we really should be exploiting to the extent that we can as large ensemble sizes as possible. And so that's really kind of the point that I want to drive here through use of the ensembles of historical simulations that we contributed that were produced using E2.2. So these were coupled atmosphere ocean historical simulations. And we're going to be looking at, each ensemble essentially consists of 750 years of integration. So these are larger ensembles that have been considered in previous studies. And we're going to be looking at these integrations to see if there's any evidence that the QBO robustly does influence these ENSO-Arctic teleconnections. And so I'm going to be focusing on two configurations. One, which is using full interactive chemistry. This is designated by OMA. And then we're going to be looking at results from a non-interactive simulation. So essentially, this simulation is driven with the 5-member ensemble average compositional forcings from the interactive ensemble. So this is not going to be capturing any QBO-induced compositional anomalies that arise in the model. So next slide, please. So I'm just going to, for sake of brevity, I'm just going to be focusing on one metric of these teleconnections. So here what we're looking at are anomalies in boreal winter 500 hectopascal geopotential height during El Nino. The top panels show what these anomalies look like during QBO West, and we have QBO East in the bottom panels. And if you'll just note the top right-hand corner in each figure denotes the number of events that are included in each composite. So if we compare to previous studies, this does actually represent a significantly larger number of events included as a result of these larger ensembles. So in the middle panel, we have results from the non-interactive version of E2.2. So this again is the free-running high-top version of the GIST model. And then we have the interactive results shown in the right-hand panel. And then what I've also included are results from a 10-member ensemble that was generated using the low-top version of the model, except that the stratospheric flow was nudged to MERA 2. And so just what we can see by looking through all the figures is that there definitely is a modulation of the Arctic geopotential height anomalies, namely that they're more positive during QBO East as compared to QBO West. We compare the bottom and the top. And so this is represented in all configurations of the model. And so we can also see that if we compare the middle and the right-hand panels, that both the non-interactive and interactive versions are capturing this, but that the amplitude of this response is much larger in the version of the model that has the interactive composition, namely ozone feedbacks. The next slide, please. So we can see kind of a similar thing during La Nina, except now we have anomalous negative geopotential height during QBO West as compared to QBO East. And again, although while in the non-interactive version of the model, this difference is not statistically significant, we do see a much larger signal during QBO West in the interactive runs. The next slide, please. So we can just ask briefly, are these geopotential height anomalies embedded in some part of a structure that includes the stratosphere? And so we can look at that by looking at these pressure latitude plots of the QBO West minus QBO East anomalies in the zonal wind for El Nino on the top and La Nina on the bottom. And again, I'm showing the results from the nudged ensemble on the left. And we have the non-interactive and interactive versions of the free-running model in the middle panels. And then just for reference, I'm showing the same composites that were generated using an older version of WACM in this previous study. And so basically, these height anomalies in the troposphere are connected to an overall strengthening of the polar vortex during QBO West relative to QBO East. We can see that feature is captured in the high top version of the model shown in the middle panels. We can also see too that the strength of that vortex is increased when we have ozone feedbacks. And even for the case of La Nina, you can see that the descent down into the troposphere is enhanced. But again, touching on some of the comments that were made yesterday, we can see, Yaga had hypothesized that perhaps one reason why models might be underestimating or not not demonstrating the role that the stratosphere plays in tropospheric predictability is because of a failure to capture certain teleconnections. What we see here is that even though qualitatively these teleconnections are being captured, that the amplitude of those teleconnections is weaker in the free-running model. And so here we see that, at least for the case of the GISS model, these teleconnections are more weakly represented, and that this is occurring in the stratosphere. So this points to a potential new area or new focus for model development. So I'll just, before passing this back to Ron, I'll just briefly comment. If you look at the leftmost bottom panel, we can see that even though I've been focusing really on the QBO vortex to tropospheric height anomaly connection, we can see that the QBO can potentially also influence the troposphere more directly through the actual extension, the direct extension of the westerlies into the troposphere. And so that feature is not being captured in the free running model, which suggests kind of a second point in which we should, before making any decisive statements about the role that the stratosphere plays in tropospheric predictability, we should really be kind of questioning, how these teleconnections are represented in models. So with that, I'll go back to Ron for the last bit. Thanks.
Okay, thanks, Clara. So finally, I want to talk about variations in the Atlantic meridional overturning circulation in some of our SSP runs. It's been known in the literature for a long time that the AMOC is vulnerable to high latitude freshwater forcing. On the left here is a plot from a paper by Ivan Matevsky that came out in GRL this year. And it shows the response of AMOC in various CMIP5 coupled models to abrupt quadrupling of CO2. And you can see that in most of the models, there's a marked reduction, if not a nearly complete collapse of the AMOC strength with time in response to the warming. One interpretation for this is that you have more water vapor, more water vapor in the atmosphere. There is a greater latent heat flux to high latitudes, and that this results in greater high latitude precipitation, which freshens the North Atlantic. I want to mention that in more gradual warming scenarios associated with the SSPs, the AMOC also generally weakens, and there's some couple of papers that show this. Whether or not the AMOC collapses seems to require sufficient forcing or sufficient warming. So this shows results from actually from Ivan's paper again, basically in for two models, GISS E2.1G and the CESM large ensemble model, and it shows that basically if you abruptly increase CO2 by some constant, then for larger values of that constant, you are more likely to see a collapse. So, for example, for the GISS model, if we basically increase CO2 by a factor of 1.5 or 2, we don't really see any long-term change in the AMOC strength. However, for 3 times CO2, we actually again see a near collapse of the AMOC. The CESM is similar in terms of its behavior. You just have to go a little bit higher, push it a little bit harder to get a full collapse. You have to go up to about 4 times CO2. Okay, one of the things that makes the AMOC vulnerable to change is that there are a couple of positive feedbacks that have been well known for a long time. So one of them is that a weaker AMOC basically will deliver less salt from lower latitudes, from the subtropical gyres and the tropics to the Labrador Sea, where sinking would otherwise occur. And this otherwise, this stabilizes the upper ocean and basically reduces the possibility of convection and reinforces the weakening of the AMOC. The reduced heat delivery into the Labrador Sea by the AMOC, if you have a weakening, will basically cause cooling, which will reduce evaporation and salinity. And this is basically the Warren idea as to why we don't see deep convection in the tropical, in the high latitude Pacific Ocean. Just to point out, these feedbacks, they basically work in both directions. They will reinforce either a weakening or a strengthening of the AMOC. Okay, so this is the key result from our model that I want to describe to you. Essentially, it shows the AMOC strength in a 10-member ensemble of simulations throughout the historical period, continuing on through SSP to 4.5, that scenario. All these ensemble members show a fairly steady AMOC. I plotted it at 48 north here. All these ensemble members show a fairly steady AMOC throughout the historical period. They show a fairly consistent decline throughout the 21st century, the current century. Thereafter, what starts happening is individual members start recovering or showing rather unpredictable recovering until by the end of about maybe over the course of the next 200 years, by the end of that period, only 2 models basically still show a collapse of AMOC. What I want to mention is that more strongly forced scenarios like SSP 8.5, collapse occurs for all members. There's no recovery. Okay, we're interpreting this to mean that there, oops, hello?
2 minutes left.
No problem. Okay, so we're interpreting this to mean that the model is near a threshold, and a lot of previous modeling work has shown that there does seem to be a threshold. I just want to emphasize that for these 10 ensemble members, this is the same ensemble. It's an identical model in all cases. The forcing is the same in all cases. So the divergence of outcomes, it's really not due to either forcing or model physics. We're interpreting this as basically just due to stochastic noise or just high frequency variability in the North Atlantic, which by itself will push you across a threshold or not. Okay, so there are a number of questions that we have left. We would like to basically identify a diagnostic that tells us if one of these ensemble members is about to recover. That seems like an important question for observations. Unfortunately, we have struggled to do this so far. Partly, this is because the transitions are really obscured by more high frequency variations in AMOC strength, which is basically shown by the gray curves in the background. As to why this happens after 2100, I think the reason is that, at least part of the reason is that the forcing variations in SSP 4.5 are weak after 2100. And this is when the majority of the ensemble members begin their recovery after this period. I think kind of an interesting question is how close is the observed AMOC from any threshold? And that raises the question of what is the relative importance of forcing versus internal variability. I don't think either of those are very well characterized. But that said, these are some of the questions that we are working with, right, or that we're working to understand right now. So thank you very much, and I'll take questions if anyone has any.
Great, thanks very much. Do we have any questions for Ron or Clara?
John, this is June. Can you hear me?
Yes.
Oh, I have a quick question for the first speaker. You mentioned seasonal forecast with the analog. I'm aware NOAA NCEP Climate Prediction Center has been using analog for operational seasonal forecast for many years. They even use a constructed analog to overcome the issue of limited data record. I wonder how your method differs from CPC methodology.
So, so my understanding, actually, Nathan is in the audience, so he could correct me if I'm wrong. But basically, my understanding is we're basically just replicating the methodology of Weeding et al. Again, I think what's interesting about this, for us at least, this is the model we're using, which is a CIMA class model, was not designed really for forecasting at all. But essentially the method is just the same. The library of analog states is just coming from our long PI control run.
Okay, thank you.
And any other questions?
I had one, John.
Okay, yep.
Yeah, a quick question. With this plot, are you essentially imposing the SSP 245 for scenario forcings up to a certain point? And then you are taking it away? Is that what you are doing in these simulations, in the recovery simulations?
So we're not, I'm sorry. So we're not taking it away. My understanding is we're basically just we're just holding it constant at the conditions that exist at the end of the scenario.
Okay, so they are imposed up to 2100, and then they are at that level staying constant. Okay.
I believe that's true. Although Susanna might be able to correct me.
Okay, any further questions before we move on to Doug Smith? If not, can we switch
All right,
presentations? Thanks, Ron. Thanks, Claire. All right, I see Doug Smith.
Okay, just sharing the screen.
I see me.
Okay.
There we go. That's better.
Almost there.
Great.
Okay, can you see that in full presentation mode?
Yes, that looks great.
Brilliant. Okay.
Oh,
Right.
Can you click the hide button?
Yes. Ah.
Oh, that didn't do what I hoped it would do.
Yep, that should
There
be
we
there.
go. Okay, great.
All
That
good.
was great.
Fantastic. Thank you. Thank you very much for inviting me to give this talk. So yeah, I'm going to talk about the signal to noise paradox in climate science. And the take-home message is there's good news, which is that the climate, especially in the North Atlantic, is much more predictable than we previously thought. And the bad news is that there is a serious deficiency in climate models. Okay, so I'm going to start off with projected trends, 30-year trends. This is from a paper by Clara Dessa. And this shows two different ensemble members from the large ensemble, and it's the projected trend for the period 2016 to 2045. The contours show sea level pressure, and the colors show trends in surface temperature. So the left-hand plot shows a trend towards a negative North Atlantic oscillation with high pressure over Iceland, low pressure over the Azores, and cold temperatures over Northern Europe. Whereas the right-hand simulation shows the opposite, basically, a trend towards a positive North Atlantic oscillation. And the only difference between these two model simulations is that they differ by tiny perturbations to the initial state, initial conditions. So the conclusion from these predictions would be, or projections would be, that there's huge uncertainty, and that this uncertainty is irreducible because it's due to unpredictable internal variability. So now, if we look at decadal climate predictions in the same way, we would actually arrive at the same conclusion. So what I'm showing here in the black line is the observed time series of 8-year running mean North Atlantic Oscillation Index. So you can see that there was an increase from the 60s to the 90s, and then a decrease after that. And then in the pink shading and the thick red line, we show decadal hindcasts, years 2 to 9 from these hindcasts. From a large ensemble, CMIP 5 and CMIP 6 together, there are 14 models, 169 ensemble members. And the pink shading shows the total, or the 5 to 95% uncertainty range from these hindcast simulations. And the thick red line shows the ensemble mean. So the ensemble mean shows virtually no signal, and the hindcast simulations essentially just about span the range of the observations, suggesting that there's no real predictability in these hindcasts. And if we look at the extreme period, just before the 1990s, where the observations showed a very strong warming signal over Northern Europe, again, we can find some ensemble members that reproduce this signal and others that have the complete opposite. So very similar conclusions from the 30-year climate projection simulations. But the thing about decadal predictions is we can assess them more thoroughly against observations. So if we do that, so the plot on the left is the one that I just showed you, the raw model output, and the plot on the right, the red line is exactly the same as the plot on the left, except that it's been scaled to have the same variability as the observations. And now that you can see that there is a signal in these model simulations, there is an increase from the 60s to the 90s and a decrease after that. And in fact, it correlates very highly with observations. The anomaly correlation is nearly 0.8. But there's a discrepancy here, because a correlation of 0.8 should explain 62% of the variance, of the observed variability. And clearly, if we just take the models at face value, then the variability that's actually explained by that ensemble mean is much, much less than that. So the magnitude of the ensemble mean variability, the raw ensemble mean variability, is inconsistent with the high correlation skill. There's also little agreement between ensemble members, which shows that that these are not alternative realizations of the observations. So just to dig a little deeper and explain why we're calling it the signal-to-noise paradox, what we can do is we can plot the anomaly correlation skill on the y-axis as a function of the number of ensemble members that are made that are used to make the ensemble mean. So the black curve shows the anomaly correlation between the ensemble mean forecast and the observations. And you can see that it grows steadily as we add more and more ensemble members, reaching a value of 0.6. And this is for seasonal forecasts of the NAO, but the story is similar for decadal forecasts. That's okay. We expect the correlation to increase as we add more members, since we're hammering out the noise. But what's not expected is this blue curve, and this blue curve shows what we get if we substitute the observations for an individual model simulation. So if the models actually gave us alternative realizations of reality that could happen if a butterfly flapped its wings, for example, then we would expect the blue curve and the black curves to be the same. But in fact, the predictability in the model world, so the model predicting one of its own members, is much, much lower than it is for the models predicting the observations. And this is a paradox because the models perfectly represent themselves and are an imperfect representation of the real world. So logically, we would expect them to predict themselves better than they predict the real world. And in fact, it's the other way around. So this shows that model members are not alternate realizations of what could have happened in the presence of chaos. It shows that we need a very large ensemble to predict, to extract and to extract the predictable signal. And this really undermines the basis of ensemble prediction. So although we called it a paradox, it's actually, there's quite a simple explanation, I think, interpretation of this. So in this schematic, the red curve shows an idealized signal. That's what we're trying to predict. This is the predictable component, if you like. And on top of that, there will be some noise to give us the black curve, such that the total variance, sigma squared, will be bigger than the variance of the predictable component, okay? So if this is what it looks like in the observations with a large predictable component compared to the total variability, in the model simulations, it actually looks much more like the plot on the right, where we have a very small predictable signal compared to the total variability. Now, it's important to note that the total variability, sigma squared, is the same in both the observations and these model simulations, but it's the fraction of this variability that's predictable that is too small in the model simulations. And it turns out we can quantify this error by looking at what we've called the ratio of predictable components. So what we're trying to do, so if the red bit in the middle is the predictable fraction of the predictable signal, compared to the total variability, we're trying to compute the ratio of the variability that's predictable compared to the total variability. So it turns out that you can do that by assessing models against observations. So the correlation squared, in fact, is exactly this. It's sigma squared of the predictable signal divided by sigma squared of the total variability. And we're just taking the square root of that for convenience. So we're defining this predictable component in the observations as the correlation that we can get between the model ensemble mean forecast and the observations. And this will be a lower limit, because if we can achieve that correlation right now with imperfect models, then we would expect it to increase as the models get better. In the model world, we can assess the predictable signal, which is the variability of the ensemble mean of a large ensemble. And then the total variability is the standard deviation of the ensemble members, the total standard deviation of the ensemble members. So that's one way to assess this predictable component in the model world. I should just say another way to do it is actually to calculate the correlation between the model ensemble mean and individual model members. That's an alternative way of defining this. So then we can take the ratio of these predictable components, and if everything is okay in the models in the model simulations, then this ratio should be 1. In other words, the predictable component in the observations and in the models is the same. If this ratio is less than 1, then the models are overconfident, and this has been the case in seasonal forecasts of El Nino, for example. But what's new, I think, in these results is where this ratio of predictable components, the RPC, is greater than 1, and this shows where the predictability in the real world is actually greater than it is in the model world. And then we can go one step further if we want to know whether the error lies in the signal or the noise, for example. It turns out that if the total variability is the same in the model and the observations, then this ratio of predictable components actually gives us a ratio of predictable signals, showing that the error is in the signal in the models. So if we return now to this time series of the NAO that you've seen before, it turns out we can calculate this RPC statistic. It turns out to be greater than 10. So in other words, the model signal is an order of magnitude too small compared to the observations. And so what that means is, because as we add ensemble members to extract the signal and get rid of the noise component reduces. It's the variance of the noise that reduces linearly with the number of ensemble members that we add. So if the standard deviation is 10 times too small, then we need to inflate the ensemble by 100 times more members than we should do if we had perfect models to extract the predictable signal. So just to highlight that, so there's this zigzag curve here, the thin one, is the ensemble mean of 169 members. It does have some skill, but there's still an awful lot of noise, even with 169 members. But if we gather together 4 start dates at a time, we can increase that ensemble size to more than 670 members. And if we do that, that's when we get the even higher correlation of 0.8 and this smooth red curve. Okay, so I mentioned this RPC statistic. We can plot maps of that to see how widespread the issue is. So if we plot maps of that for year 2 to 9 forecasts, we've got plots for temperature on the left, precipitation in the middle, and sea level pressure on the right. What we can see is that on these decadal timescales, this is a widespread issue, even for surface temperature. The RPC is greater than 1 in most regions, actually. And then when we look at precipitation and sea level pressure, we can see the red colors get darker, showing that the error is even bigger for these other variables that are related to atmospheric circulation. So it's really atmospheric circulation that's underestimated by the models. Okay, so I've highlighted decadal scale predictions so far, but this issue is also seen on other timescales. It was first seen actually in seasonal forecasts of the North Atlantic Oscillation, the NAO. And this paper by Laura Baker shows that all of the operational seasonal forecasting systems that she looked at, so several of them here, suffer from this signal to noise paradox, with the RPC plotted on the y-axis extending to values greater than 1 as we add more ensemble members. The only one that doesn't suffer from this problem is the ECMWF model, but then that's because it doesn't have any correlation skill with the observations. We also see it in seasonal forecasts of summer European rainfall. So again, the plot on the left shows the raw model forecast. So the red line is the ensemble mean, and the dots are individual ensemble members. So again, taken at face value, we would think there's little ability to distinguish between positive or negative values of the summer rainfall. But if we scale this ensemble mean forecast, now we find that there is actually a significant correlation, nearly 0.5, between the ensemble mean and the ensemble members. And it turns out that this RPC statistic is 5 in this case. And Steve Yeager has also shown that on multi-year annual timescales, European rainfall is also predictable, but again, it suffers from the signal to noise issue. And then we can look at Sahara rainfall predictions, multi-year predictions of Sahara rainfall. I think this is years 1 to 5, if I remember rightly. This is again from Steve Yeager's paper, but it's also shown by Katie Sheen. So if you look at the raw model data, again, the curves show little variability compared to the observations in black there. So this is the ensemble mean forecasts. But if they're scaled, again, they do a much better job at picking out the observed variations. And in this case, the RPC was 2. We see it also on subseasonal timescale. So this paper shows the teleconnections between the MGO and I think it's geopotential height over the northern hemisphere. So the top plot shows the observations, and then we have the same teleconnection patterns from a range of models from this subseasonal to seasonal forecasting system. And all of these models underestimate the strength of this teleconnection compared to the observations. And then this paper by Daniela Dominson, they calculated the RPC statistic directly in these subseasonal forecasts, and this shows the RPC in colors as a function of forecast lead time in days. So you can see that this, so anything greater than 1 is showing where the signal-to-noise paradox is starting to occur. So you can see that it's starting to occur mainly in the troposphere, but even after just 10 days, and then it grows and spreads up into the stratosphere. So there's also some evidence that models may underestimate the responses to external factors. So this plot on the left shows a multi-model response to volcanic eruptions, and it's in the first winter following a volcanic eruption. It's an aggregate over several or 3 volcanic eruptions. So the colors show the heating response. So you can see there's heating in the stratosphere due to the aerosols that have been released by the volcanoes. And the contours show the zonal wind response, showing a strengthening of the polar vortex following the volcanic eruptions. So the top plot shows the average from multi-model simulations, and the bottom shows the same thing diagnosed from reanalyses. What you can see from this is that the heating appears to be about right in the model simulations, whereas the response in the winds is much weaker than is seen in the reanalyses. And then on the right here, we have some evidence that models may underestimate the response to the 11-year solar cycle. So on the left, we have some diagnosis of the response, sea level pressure response to the solar cycle in observations. And you can see that this response peaks at a lag of about 3 years with a positive NAO type structure. Whereas in the model simulations, the total response is weaker than in the observations, and also there's not the lag that's seen in the observations, suggesting that there's there could be some errors in the ocean atmosphere feedback in the model simulations. And then a recent study also showed that if we just look at externally forced simulations now, then we also see the signal-to-noise paradox. So again, this study shows in black the observed time series of 8-year running mean NAO, and then in red, the red line is the ensemble mean from a very large ensemble of externally forced simulations. So there's no initialization in these runs at all. And again, they show a correlation with the observations. I think the pink shading shows the raw ensemble spread, and the line shows the signal after some scaling. And then on the right, too, again, we have this plot where we see the correlation skill versus the number of ensemble members, and there's been up to 500 included in this analysis. And the grey is the skill against the observations, and the blue is the skill against an individual model ensemble member. And then this ratio of predictable components again is greater than 10 in these externally forced simulations.
2 minutes left, Doug.
Okay, thank you very much. So I just wanted to highlight that if we want to predict the NAO impacts or assess the impacts of the NAO, So I've I've highlighted that we can extract the signal by taking the mean of a very large ensemble, but that's not quite true if we want to know the impacts of the NAO, and that's because if we consider Europe, for example, then it's affected by greenhouse gases as well as the signal from the NAO. But in the ensemble mean, the NAO signal is too small, so what we're left with is the impact from greenhouse gases. So what I'm showing here is this peak NAO decade in the 1990s with a clear warming signal over Northern Europe. As expected, the raw model ensemble doesn't show this signal, but even if we standardize it, we still don't see the desired signal, but we can extract these NAO impacts if we select the ensemble members that have the correct NAO amplitude. And if we do that, then we start to see temperature signals in line with the observations. So why do we write about this? Well, it has lots of impacts in terms of how do we measure skill. Probabilistic skill measures that rely on the ensembles shifting will miss the potential skill that could be available. As I mentioned in seasonal forecasts, the problem's typically been the other way around, where the models have been overconfident and there's been some development of stochastic physics schemes to increase the spread. But for these predictions where the models are underconfident, then this could potentially exacerbate the problem. Sometimes in previous studies, we've looked at perfect model predictability experiments and thought that they would give us an upper estimate of the predictability, but that's not the case if the signal to noise ratio is too small. It has implications for event attribution. So if we run models forced by observed sea surface temperatures, for example, and they don't respond correctly to the sea surface temperatures, then we won't be able to get the correct changes in the probability of extreme events. It affects estimates of unpredictable internal variabilities, as I highlighted in the very first slide. So if the models are not responding correctly to the external forcing factors, then the diagnosed internal variability will be too large. But we can make skillful forecasts by taking a very large ensemble. But if we could resolve this issue, this error, then we could reduce our ensemble sizes and increase prediction skill potentially. So just to summarize then, so there's widespread evidence in climate models that they underestimate signals, especially related to atmospheric circulation. This is seen on multiple timescales in different seasons, winter and summer. So timescales ranging from sub-seasonal up to multi-decadal. It's seen in multiple variables, temperature, rainfall, pressure in different regions in the exotropics, but even the tropics on longer timescales, decadal timescales. And it appears to be caused by multiple different drivers as well: internal variability, solar and volcanoes, potentially greenhouse gases. We're not 100% sure about that. So it affects estimates of skill. But I think the key question now is what are the implications of this for attribution, for understanding what's caused decadal scale climate variations, and does it affect regional projections of the coming 30 years or so? So thank you very much, and I'll stop there.
Great, thanks a lot, Doug. So we have several questions in the chat that I'll start with. First is by Chris Roberts. He says, is the time averaging, e.g. seasonal multi-annual mean, a crucial component of this paradox? It should have a similar impact as ensemble size to reducing noise and ensemble mean on the increasing RPC. For example, I can't see any evidence of a paradox in ECM WF and AO predictability. It leads 1 to 35 days using daily indices, RPC, potential predictability, etc. are self-consistent. Any comment?
Okay.
So,
I mean, we are looking for something that can be predicted. So, generally, as we increase the time averaging, then we do find stronger predictable signals. So that could be part of the issue. I'm not sure I've totally understood the question. Sorry, Chris.
So Gavin makes a comment: the volcano solar examples are not distinguishable from the uncertain forcings and ozone mechanisms. And then Ram asks, in the volcano example, isn't there a need to look at the base state also to assess the prediction of the northern hemisphere polar stratospheric circulation?
Okay, I'm not quite sure what you mean by that. I think that there's certainly some evidence that ENSO connections can play a role here, but we've tried to take those out. You know, these results are not definitive. They're just further evidence that points in the direction of underestimate of the model atmospheric signals.
Okay, we have a hand up from Ela Simpson.
Hi, yeah, I was wondering about those kind of synthetic time series that you showed to depict the difference between the noise and the signal in between the models and the observations. And there was kind of a clear separation of timescale, which kind of suggested if you filtered in different ways, you should see differences in the variability between the models and the observations. I was wondering if that's kind of a real, what you intended, or is it just kind of for ease of depicting schematically the differences?
I'm not sure I totally understand the question. Are you saying that if we assess model simulations in a different
when
way,
you showed those, yeah, I guess it would be easier to see the time series, but you had the kind of sine curve that was like the signal, this. So like, for example, in this case, if you did some kind of high pass filter, you would expect to see much higher variance in the models than the observations, and vice versa if you did a low pass filter. But is that, do you think there really is kind of a separation in time scale of the unpredictable and the predictable parts, or not?
Well, there could be. That might be an interesting thing to try, perhaps.
Yeah, I think it would be.
I mean, it is just a schematic, but yeah.
Yeah.
We need to move on to Chris Roberts. Thanks again, Doug.
Thank you.
Lots of food for thought. Great, we can see your...
Okay, can you hear me?
We can hear you.
Brilliant.
We cannot see you, but we can hear you.
That's fine. Okay, good afternoon, everyone. Firstly, thank you for the opportunity to attend and talk at this workshop. For those that don't know me, I work in the Earth System Predictability section at ECMWF, and I have a focus on our extended range subseasonal system. So today I'm going to present some recent work on the impacts of resolution and SST biases in our system, which has been done in collaboration with many different colleagues at ECMWF. So I'll touch on a few different topics today, including a quick overview of our coupled forecasting system, a summary of the impacts of ocean and atmospheric resolution from climate simulations we did for high-res MIP, the timescale dependence of these impacts with a focus on the ocean, and a short note on the continued value of lower resolution models, even as we move towards higher and higher resolution configurations. And I'll finish with some results on a recent study showing the impacts of the Gulf Stream in our subseasonal forecasts. A couple of things I won't talk about. I won't discuss explicitly short or medium range coupled NWP. I'm going to focus on the S2S to climate timescales. I won't discuss explicit convection resolving kilometer scale atmospheric simulations, but if you are interested, you should see the recent paper by Niels Veddy and others, which was recently published in James. And I don't have any results from eddy resolving or eddy rich ocean model configurations. This is going to be a focus over the next few years at ECMWF, but we're not quite there yet. So for those not familiar with it, this is a schematic of the ECMWF integrated forecasting system. An important thing to note is that all of our operational configurations are coupled to a dynamic ocean model, an ocean wave model, and sea ice. The resolution of the atmosphere varies from about 9 kilometers to 36 kilometers, covering the medium range to seasonal lead times. And at all of these lead times, we use the same 25-kilometer eddy-permitting ocean sea ice model, NEMO. As well as running these initialized forecasts, we've also run Ensemble climate simulations following the CMIP6 high-resmit protocols. These are based on IFS cycle 43R1, which is the same model as our current seasonal forecast system. These experiments include both coupled and AMIP configurations and were run for a range of different ocean and atmosphere resolutions. These model configurations and the scientific assessment is documented in a paper that was published in GMD a couple of years ago. And all of the CMORized ensemble output is available with other CMIP6 data through the ESGF. So the next couple of slides are going to focus on the impacts of atmospheric resolution in these high-resmit AMIP simulations. So generally speaking, increasing resolution of our atmosphere from about 50 kilometers to about 25 kilometers has an extremely limited impact on the mean state and the large-scale variability. These plots on the left show the mean bias in 2-meter temperature and precipitation in these different AMIP experiments, and I mean, they're effectively identical. On the right, we have these are plots of Northern Hemisphere teleconnections in geopotential height associated with variations in precipitation in the tropical Indian Ocean. And again, it's extremely difficult to tell these apart given the sampling uncertainties. One notable exception is the magnitude of a cold bias in the lower tropical stratosphere. So this is highlighted here with this red box. Which is generally degraded at higher horizontal resolutions. This bias is related to errors associated with vertically propagating gravity waves, which become more active at the higher horizontal resolutions, and it's improved if we increase vertical resolution. And this bias is one of the motivators for a recent increase in the number of vertical levels of our ensemble system from 91 to 137 levels. And there's lots more detail in this in some of the tech memos by Ina Polachuk et al. Available on the CMWF website. So although there's this limited impact on the mean state, increasing resolution does have a clear impact on the representation of the weather and extremes. So this example shows composites of tropical storms from our climate simulations, and they're stratified by intensity. And it's clear that higher horizontal resolutions result in both more frequent and stronger tropical cyclones, which is something we know from NWP. And there's some other examples of the impact of horizontal resolution on extremes can be found in some other papers that were written as part of this Primavera European project using output from high-resmit models. So in the next few slides, I'm going to focus on ocean resolution in coupled simulations. And in contrast to what we find for atmospheric resolution in the IFS, it's extremely sensitive to an increase in ocean resolution from around 100 kilometers to 25 kilometers. So this is a transition from this eddy parameterized to eddy permitting regime. Almost all aspects of the coupled system are affected by this change, including the atmospheric biases, the variability, and the air-sea interactions. In general, the eddy permitting simulations are much improved. In particular, there's a reduction in this severe North Atlantic cold bias, which in the low resolution model is associated with a very weak Atlantic overturning circulation and much weaker meridional heat transports and associated sea ice coupled feedbacks. Another example is shown here at the bottom is the improvements to equatorial Pacific precipitation biases with the higher resolution model. The notable exception is an increased warm bias in the Southern Ocean, which is degraded significantly in the eddy permitting ocean configurations. So, although we see this very strong sensitivity to resolution in the ocean, the impacts are really sensitive to the timescale or the lead time you're interested in. So some of these impacts, such as the strength of air-sea interaction in western boundary currents, they're immediate and they're there at all lead times. Others, like the SST biases, take time to develop and are obviously strongly mitigated by initialization. So these plots on the left show the impact of ocean resolution in some subseasonal and seasonal reforecasts, and fully developed biases in climate experiments. So at the S2S timescales, the Atlantic errors are dominated by a warm bias associated with errors in the separation of the Gulf Stream, rather than this cold bias you see in the North Atlantic subpolar gyre. And one thing it's very difficult to do at this S2S timescale, it's very hard to show any impact of this big difference we find in the strength of air-sea interaction. So for example, in our climate runs, we see large differences in both blocking over Europe and the intensity of the storm track, which is much improved at the 25-kilometer ocean. But we see almost no change in our S2S models. So this is suggesting that it's these differences in the large-scale biases rather than the differences in the air-sea interaction that are most important for these aspects. That said, S2S scale over Europe is improved in when we run with a higher resolution ocean. But this seems to be driven more by improvements to the tropics and the MGO and the strength of these teleconnections rather than any changes in local air-sea interaction. And sorry, this slide, it's a bit of an aside, but I think even though I believe that eddy resolving and eddy-rich ocean models are the future, they're very expensive and they won't completely replace these lower resolutions. So I think we'll still, there's still a future for well-formulated eddy parameterized, eddy permitting ocean configurations, especially at ECMWF, where we use them for a variety of research, testing, and development applications. So although the absolute model performance is better at higher resolutions, it's often less relevant than the difference, the delta between two experiments. And although it depends on the metric, the delta you estimate with a low-res model might be a very good proxy for the delta you estimate with a higher resolution ocean. And that's particularly true at short lead times when the biases are very similar. So this just shows an example of some summary scorecards estimated for a recent IFS cycle using on the left a 25-kilometer ocean and on the right a 100-kilometer ocean. So in this particular case, you get a very good idea of the impact on our operational system from using a much cheaper ocean model. And there's lots more details in this tech memo on our website. Okay, for the remainder of this presentation, I'll discuss some recently published results based on sensitivity experiments with our coupled forecast system. So although we know that ocean atmosphere coupling can improve skill at subseasonal lead times, it also introduces this potential for systematic errors, especially in the sea surface temperatures. And again, as we saw in an earlier slide, the ECMWF model, it doesn't fully resolve the ocean mesoscale in the mid-latitudes. And therefore, we can't accurately simulate the separation of the Gulf Stream from the North American continent. The work I'm going to present now shows how that if you artificially correct these SST biases in the North Atlantic, we can improve subseasonal skill, both in the Atlantic and Europe, and also in remote regions as signals propagate along the tropospheric waveguide. So a few years ago, Minobi and others demonstrated that the Gulf Stream is associated with this pattern of near-surface wind convergence and upward motion that anchors this band of precipitation along the warm edge of the Gulf Stream. And they also showed that this response extends throughout the troposphere and can influence remote regions by forcing planetary waves. More recent studies, of which there's been a few, there's one example here at the bottom, I've really emphasized that this relationship between the SST gradients and the atmosphere is a consequence of the accumulated aggregated impact of atmospheric fronts interacting with sharp SST gradients as they propagate in the Atlantic storm track. So any SST bias in our forecast model that modifies the position of the Gulf Stream, it then has the potential to impact both the location, the magnitude, and also the timing of where we're getting vertical motion and convection associated with storms. And there's been several idealized model studies showing that atmospheric errors can be that can be explained by biases in North Atlantic SSTs. For example, this paper by Robert Lee and others imposed SST biases from a coupled simulation in an AMIP version of the same model. And these heating anomalies cause spurious vertical motion and stimulate this planetary wave response that propagates throughout the entire Northern Hemisphere. However, this and lots of the other studies have either focused on very heavily smoothed observed SSTs or fully developed biases from climate models. And in the work we've done, we emphasize that even at short lead times, errors in the position of the Gulf Stream can also have a significant impact on atmospheric forecasts at subseasonal lead times. So the way we do this is we have run our coupled forecast system, two different reforecasts with our coupled system. Firstly, we have control, which is our reference reforecast, which we use to evaluate SST biases as a function of location, start date, and lead time. And then we run this bias corrected forecast, in which the ocean receives the atmospheric fluxes as normal, but in the North Atlantic, the SSTs seen by the atmosphere are adjusted at each time step using the SST bias we derive from the control. In both cases, the ocean and atmosphere resolution is around 25 kilometers, and the reforecasts cover the extended winter period over the years 1989 to 2015 to give a total of 270 start dates of 15 members each. So on the left here, you can see that the largest SST biases in our control experiment are associated with these errors in the position of the Gulf Stream. And they also impact errors in the heat fluxes, which here in the middle is the surface latent heat fluxes. And these errors are effectively reduced or eliminated in our bias corrected forecasts. And here you can see the difference between the two experiments, with the yellow box in the top right indicating the domain of the SST bias correction. And these differences in the SSTs and the fluxes also impact 2 meter temperature, convective precipitation, and also the vertical motion, with the warmer SSTs associated with more precipitation and more vertical motion. This figure is a sort of a summary scorecard showing the quantitative impact of this SST bias reduction on the mean state for a range of different variables as a function of lead time and region. The blue triangles indicate that there's a reduction in the mean absolute bias integrated over grid points and start dates. So you can see that the improvements to the near surface fields are fairly clear at all forecast lead times, particularly in the Gulf Stream region. However, other than the changes to the vertical velocities and the convection actually over the Gulf Stream, the impact on the upper atmospheric mean state is extremely limited. So nevertheless, these changes to the mean state of the vertical motion and the convection, they still have consequences for the predictability that extends beyond the North Atlantic domain. And that's what's shown on this slide, which is another summary scorecard, but now this is summarizing the impact on probabilistic forecast skill, again as a function of region, and weekly lead time. So here the blue triangles indicate an improvement in the continuous ranked probability skill score, again aggregated over grid points and start dates. So although we saw this limited impact on the mean state, the reduction of the SST biases still improves forecast skill at week 4 of these atmospheric circulation anomalies. And these impacts extend beyond the North Atlantic and actually circumnavigate the globe along the Northern Hemisphere waveguide. And another interesting feature is that the impacts over Europe are really only evident when we have an MGO in the initial conditions. We can also look at these impacts in terms of the North Atlantic oscillation. So this is showing, these are daily indices, this is anomaly correlation skill for the NAO as a function of lead time for daily NAO indices. And again, you can see that the reduction of North Atlantic SST biases leads to improvements in NAO skill for sort of weeks 3 and 4. So this slide now emphasizes that this atmospheric response is not just limited to the North Atlantic and its immediate surroundings. We see in shading, it's the change in the CRPSS, and the contours are the changes in the correlation score. And you can see that this signals propagate, the way these signals propagate is characteristic of actually barotropic stationary wave activity. And it's steered along this waveguide defined by the meridional gradients of absolute vorticity. we interpret this as evidence that this southward shift in the Gulf Stream is changing where and when we're having forcing from extratropical storms. So where and when we're getting this vertical motion, which is then forcing planetary waves which propagate in the upper troposphere. Okay, so in summary, in the ECMWF model, other models, you might get different answers. Increasing atmospheric resolution from about 50 to 25 kilometers impacts the weather and the extremes, but the response of the mean climate and the large scale variability is actually rather limited. In contrast, if we increase the ocean model resolution from 100 to 25 kilometers, so going from parameterized eddies to an eddy permitting model, we see a dramatic impact on the coupled system, but the impacts really depend on the timescale, and the SST biases can take a long time to establish. In our subseasonal system, our forecasts suffer from errors in the North Atlantic, which are associated with biases in the biases in the location and also the structure of the Gulf Stream. If we correct these errors with an online SST bias correction, we can improve the mean state of the North Atlantic, but we also see a significant impact on remote atmospheric circulation anomalies. And so these impacts provide important evidence to us that there is going to be some benefit to having an initialized coupled forecast system with a much higher resolution ocean, one that can better resolve the position of the Gulf Stream and sort of both initialize and maintain accurately these mesoscale features in the North Atlantic. That said, we do an awful lot of testing and run an awful lot of reforecasts, and we can never run them all with eddy-rich or eddy-resolving oceans. So lower resolution models will continue to have value for us for research, for testing, for development, and for large ensemble applications. So this is a strong motivation for both the maintenance and the development of cheaper ocean configurations that can mimic features of these higher resolution models. So for example, we're interested in testing things like stochastic physics parameterizations, models that have unstructured grids, so more of your computational effort goes in the places that you really need it, and also whether there's potential for AI or machine learning methods that can represent the rectified impact of eddies on the mean state. So that's my talk finished. This is a list of the references, so you can find further details from some of these papers and technical reports. And we've recently moved to an open access model for our data. So if you're interested in looking at these bias-corrected reforecasts, you can actually download all the data yourself from the ECMWF website. And our high-res data is also available from ESGF. Okay, thank you very much.
Great, thanks very much, Chris. I'm going to start by inviting Gavin to give his comments rather than, there's a lot of text in the chat. Gavin, can you jump in?
I mean, it's in the chat. You know, I'm very persuaded that Doug's. Sorry, like which comments are you asking about?
Well, you started off with the Linzen article, and then about ozone and solar cycle.
So ozone is related to Doug's talk, and the Linzen question that's more relevant to this. And so, so I guess I can just ask that. So, you know, Linzen and Rabinovitz had a scaling argument for why you should increase the vertical resolution as you increase the horizontal resolution. And I was just wondering whether the ratio that you've ended up with actually fits that, and the one that you had before was insufficient.
I mean, I think the one we had before was insufficient. Vertical resolution helps, but it's actually, there are other ways of addressing this related to the discretization and the numerics that are used. So before we increased the vertical resolution, we actually also adopted, I think, a higher order interpolation for the semi-Lagrangian advection, which actually helped an awful lot, having this quintic interpolation. And so some of our anticipated benefits of the higher vertical resolution didn't quite materialize because we'd already had some of it from these other changes. And there's other things going on related to the numerics that I'm not particularly familiar with, but the aspect ratio is definitely one of the arguments, yeah.
Thanks.
We have a question from Fei Yu Lu. For the subseasonal forecast with different ocean resolutions, how do the differences in ocean initial conditions especially regards to the Gulf Stream, affect the model SST drift and overall prediction?
So the differences in the initial conditions is a huge part of it, because an awful lot of these errors we see at very short lead times are directly inherited from the initial conditions used. So a very important part of the work I showed is making sure that our initial conditions for the low-res model are as consistent as possible with our high-res model. So they're actually derived from an ocean analysis at the eddy permitting resolution. If we take a native 1 degree, 100 kilometer analysis, it will look much worse.
Okay, do we have any more questions for Chris? Steve Yeager?
Yeah, maybe I missed it, but in your bias corrected reforecasts, how do you deal with ocean drift? So you're just applying a static bias correction throughout the forecast?
Exactly. So there's no accounting for sort of nonlinear interactions here. So what eventually happens is also it's only the atmosphere that sees the bias correction. The ocean model's still wrong underneath. And so eventually there is an inconsistency between the fluxes between the ocean and the atmosphere. And if you run these forecasts for long enough, the SSTs actually start to get so bad that your bias correction doesn't work anymore. So it works quite well for these lead times, but it's not something that you could use, I think, very well in a seasonal forecast.
Thanks.
Okay, any last questions before we go for our break? If not, we'll reconvene at 1:30 in 25 minutes with Ben Kurtman, chaired by Marina Molina. Thanks, everybody.
The Zoom link will stay on, so you can stay. Maria, are you on?
Yes. Hi, Gokhan.
Hi.
Hey, thanks for the opportunity.
Oh, no worries.
Did you want to say a few words before going into breakout rooms?
Yeah, I'll just say a few words. Yep.
Okay. Hi, Ben.
Hi, Maria. How are you?
I'm good. How are you?
Good.
How is Miami? That's where you are, right?
Normally, I would be in Miami, but I'm not at the moment, which is a good thing in the summer.
Are you in Portland or Seattle or something? No.
No, I'm in Southern California.
Okay.
I was going to say it's probably hotter in Pacific Northwest right now.
Probably hotter, but probably not more humid.
True. Okay, everyone, welcome back. It's 30 past the hour, so we'll go ahead and get started. My name is Maria Molina. I work at NCAR. Thank you for the opportunity to chair the upcoming session today. So our first speaker is Ben Kurtman from University of Miami. Ben, you have approximately 20 minutes, and I'll go ahead and give you a 2-minute warning. Feel free to share screen. Okay, take it away.
Thanks. So I'm going to talk a little bit about subseasonal decadal predictability and prediction using ocean eddy resolving models. People might argue with me whether the resolution is high enough to be ocean eddy resolving per se, but at least in terms of what I'm looking at, I think we're at least getting a long way there. And I definitely want to acknowledge all my collaborators listed here, and in particular, I do want to call out the NCAR Catalyst team, because I think we're embarking on a collaboration that is turning out to be really useful. Before I get going too, I also want to thank Doug and Chris for their excellent talks. They were fabulous talks, and I really enjoyed them, but also for making much of what I'm going to talk about totally irrelevant. So, just relax, sit back and enjoy, because there's a great deal of overlap from what Doug and Chris reported on. So basically 3 parts that I want to talk about. The first part, of course, is a little bit about a reduction of bias, but there are notable improvements when you go to this eddy resolving scale, particularly in eddy-rich regions like the Western Boundary Currents, the Southern Ocean, things like that. But it's definitely not a panacea. And so, in fact, if you just looked at RMS, RMS errors, the improvements are modest, but they're there. It's really feature-based. It's phenomenon-based. It's starting to look at actual processes that are going on. That's where you really see the big improvements. And the first thing I want to sort of talk a little bit about is the sort of global scale predictability and prediction, just looking at this at the largest scales. And then, of course, Doug stole my thunder, and I appreciated his talk, so it's a good warm-up. But I want to talk a little bit about this signal-to-noise paradox and what we're kind of looking at in this higher resolution, or this ocean eddy resolving, in terms of that signal-to-noise paradox. And then the bulk of the talk is really thinking about the regional climatic imprint associated with ocean mesoscale features. And there's 3 particular regions that we're going to look at. We're going to look in the North Pacific and downstream from the Kuroshio extension. We're going to look at rainfall in the Western US, where we see a significant role for actually eddy activity in the Kuroshio extension. And then in the North Atlantic, we're going to look both downstream and upstream. So there's this downstream effect, and indeed, Chris talked a fair amount about that downstream effect of actually getting the Gulf Stream in the right place. But we're also finding an upstream effect, particularly in the summer season, for low frequency variability in the southeastern US. And so I'll talk a little bit about that. And the last bullet on this slide here is I'm trying to make a point. When we first started this eddy work way back in 2010 is actually when this project started. It initially started. The expectation was, really just going to be an ocean eddy component. We really weren't thinking about climatic phenomenon that affected people's lives. And it's turning out that this, the importance of getting these ocean mesoscale features may actually affect people where they live. And so that's kind of the point I'm trying to make. So presence of ocean mesoscale features, fronts and eddies, modify ARC coupling, which affects the local representation of the predictable large-scale climatic features. So hopefully that's what I'm going to say. Hopefully that's what I'm going to show you today. So there's two models we're working with, primarily CESM and some cases with CCSM4, so the NCAR family of models, if you will, and then E3SM V1, version 1 of that. For almost everything, there's two versions of this low resolution. And some of the results were clean in the sense that we're using the same atmospheric resolution and we're comparing a 10th of a degree ocean to a, basically a 1 degree ocean. Some of the results, we've actually changed the atmospheric resolution and the ocean resolution. So I apologize for that. And I'll try to note that in just about every figure where, really which resolution version is being used. So just to start out, we published this paper in 2012, just running this 10th of a degree with a ½ degree atmosphere, 1 degree ocean, 10th degree ocean, ½ degree atmosphere, and then 1 degree ocean and a ½ degree atmosphere. And we compared them. And this is just looking at the annual mean SST bias in those two runs. And so you can see the bias is quite a bit different, particularly in the extratropics, particularly in the eddy-rich regions. But in an RMS sense, they're pretty close. They're pretty comparable. And so what I'm saying is just throwing the resolution at it is not sufficient. You need to put a lot of effort into thinking about how our parameterizations work at this resolution and all kinds of, the numerics. Is the numerics operating efficiently at this resolution? So there's still a fair amount of work to be done to even capitalize on these very high resolution simulations. And then, of course, what the most dramatic result, as expected, is just the variability, the overall variability. And so here I'm just showing you the ratio of standard deviation from the high resolution to the low resolution. This is plotted on the atmospheric model grid, so they both have the same atmospheric model, so it's genuinely a fair comparison. And you can see that as much as 3 times the amplitude of the SST variability in those eddy-rich regions, and extremely modest increases in amplitude in the other parts of the ocean. One of the results that we perhaps didn't necessarily anticipate at this was how this would affect the RC feedbacks. And what this plot is just a very trivial assessment of, although somewhat difficult to interpret, but a trivial assessment of local RC feedback. So it's just a point-by-point correlation between the turbulent heat fluxes and sea surface temperatures. It's point by point, and the top panel is from the high resolution model, and the bottom panel is from the low resolution model. And we've actually looked at this where we use the ½ degree atmosphere also, and the results are quite comparable. And so, yeah, over land, these correlations look almost identical. However, when you look over the oceans, you can really see those eddy-rich regions really pop up, where that correlation is actually in some locations totally the opposite sign. One of the easiest ones to see is in the Gulf of Mexico. In the Gulf of Mexico, that low resolution model is a negative correlation, where it's a positive correlation throughout much of the Gulf of Mexico. You can see the western boundary currents really pop, the Southern Ocean really pops using CESM. Now, looking at E3SM, we did the same calculation. We have E3SM V1. We have 2 nice simulations. They're not quite as long, but we think we think these are fairly reasonable. The popping of the western boundary currents is pretty much the same, but you can see that it's not quite as dramatic in going from the low resolution version of E3SM is going to the high resolution. In the Southern Ocean is perhaps one of those examples. I mean, the Gulis region, you can see that you had a fairly strong positive correlation in the low resolution model already. It certainly gets a lot stronger in the high resolution model, but not nearly as a dramatic result as using CESM. One of the other things is we try to use these long simulations to really sort of do diagnostic predictability along the way. And this figure is just based on a nice calculation of Grant Brandstatter's, and Haiyan Teng is also a co-author of this paper, where they looked at the variance weighted mean period in these long simulations. And we've done this with E3SM at both high resolution, low resolution, and CESM. And so you can see that you're getting a fair amount of increase in the extratropical lower frequency variability in CESM compared to E3SM, and a bigger bounce with CESM than E3SM. What's really fascinating to me about this figure, however, is in the deep tropics, E3SM is showing a lot more low frequency variability, particularly the tropical Eastern Pacific, compared to any of the other three simulations. So that's something that we're really interested in looking at and trying to understand. With reference to Doug's talk, he really appreciated how this signal to noise problem or paradox, whatever you want to call it, has gone quite a bit far from just the NAO. We're recognizing it happens at almost all scales and all time scales and all phenomena and all locations. We really do have a signal to noise problem, which is confusing given that we largely have models that are under dispersive. So it's just a very interesting problem. And what I'm showing you here on the left-hand side here, I'm just going to get out my pen here. On the left-hand side here, this is a calculation that Wei Zhang, my student, put together. He's basing this just on the CMEP5 historical simulations. He drives a Markov model for each model, and then he makes a plot of how likely there's going to be a signal to noise paradox in that model, looking at that RCP statistic that Doug talked about. And this is looking at CMEP5 from the historical simulations. And interesting, we also did it to the pre-industrial simulations also. And there's some interesting regions that are significantly different. But what's ubiquitous is that it's very likely on these decadal timescales that we have a signal to noise paradox almost everywhere in the ocean. This other panel now is, and one of the results in the Zhang paper is that persistence, how persistent the model is a critical element in that signal to noise problem, particularly on the decadal timescales. And so what we've plotted here is the ratio of the high resolution model to the low resolution model in terms of the persistence timescale. And what you're seeing here is a significant increase in persistence in the deep tropics, throughout the deep tropics, in the North Atlantic, North Pacific. And these are all regions where there's a very high or relatively high likelihood of a signal to noise problem. This increased persistence with the high resolution model in principle should decrease that signal to noise paradox. So this is a good result. Again, on these global scales, just trying to understand what is giving that enhanced persistence. And all we're plotting here is just a really simple, again, just point by point, just a local SST and a temperature from 700 to 1,000 meters. So how much is the deep ocean sort of interacting, if you will, with this very simple metric of that with the surface temperature. And of course, this panel is for the high resolution model, and this panel is for the low resolution model. And you can see in all those eddy-rich regions, there's a significant enhancement of the correlation between what's going on at the surface and what's going on in the deeper ocean. And this, of course, occurs over many different levels. I just picked the 700 to 1,000, but I could pick any number of different levels. And it's really sort of demonstrating that these low frequency timescales, there's a mechanism by which there's more communication. These eddies are largely barotropic, and how they're communicating with the deeper ocean. And then just one more figure, looking at, why are we getting these longer timescales? Now this is looking at slightly higher in the ocean, but the heat content from the surface to 400 meters and the turbulent heat flux. And so again, you can see these eddy-rich regions of the Southern Ocean, the North Atlantic, and the Pacific are really popping with much higher correlations compared to the lower resolution model. And this is just an advertisement that we're starting to do these prediction experiments that I'm going to be reporting on in just a second here. We're starting to get them done across the various models, CESM and E3SM, and this is the the control set, and we're also going to be doing that at these eddy resolving resolutions. So just a bit of an advertisement for what we're going to be doing. Okay, so the regional climatic imprint associated with these ocean mesoscale features, and again, Chris sort of really touched on some of this, so some of it is a little bit of a review. One of the points that Chris made, so this is looking in the Gulf Stream, one of the points that Chris made is that enhanced air-sea interaction happens right away. And so these are actually initialized forecasts. These are, the first set of forecasts are from CCSM-4 as part of the SubX project, and run regularly. And then this is looking at the CSM high resolution forecasts that we've made. We've made a whole suite of them for over a 30-year period from 1982 through for 30 years, the CSM forecast. And just looking again at that local correlation between the turbulent heat flux and the SST, and in some sense is a measure of how robust the ocean is actually driving the atmosphere when this correlation is positive. And what you can see is even after 1 week, right away, that correlation is really popping in the high resolution model. And then by week 4, it's really ramped up. So even on sub-seasonal timescales, that air-sea interaction is significantly affected by the high resolution. And that really wasn't our expectation. These eddies are fairly slow timescales. We did not expect that to pop right away in the forecast mode. So this is really popping right away in the forecast mode. And I should say that the initial conditions, the source of initial conditions, we use this brute force initialization strategy in these forecasts. The initial conditions come from exactly the same source in both sets of forecasts. Exactly the same set. So it's just this brute force initialization is just cramming it into that model as best we can. It's just interpolation. So if we take those forecasts, again, these are initialized forecasts, and so now we're looking at what's the downstream effect where people live. And it's my point is that having these eddies in the system. I'm not saying we're actually forecasting the individual eddies. I want to underscore that. So I'm not initializing the model so it gets the individual eddies right. We're initializing the model so it has the eddy energy correctly. That's the basic idea here. And so what we're looking at here is rainfall. And we're looking at, on the top panel, is taking 7 years of trim data when the eddies are active versus inactive, 7 years of each, and not including ENSO years. So we're attempting to remove the effect of ENSO on this, but it's arguable whether we completely remove the tropics in this calculation. So the top panel is the observations. The middle panel is then looking at those high resolution forecasts for exactly the same years. And then the bottom panel comes from the NMME forecast with CCSM 4. And so what you can see is I'm trying to highlight this downstream effect over California, real enhanced rainfall associated with how active the eddies are in the Kuroshio extension versus years that they're inactive. You get a big signal downstream. And this is just zeroing in on California. The top panel is CMORPH data, and the middle panel is the high resolution model. The bottom panel is the NMME forecast. But I really want you to look at the distribution curves because what you see is the blue curve is the distribution on those eddy active years, and the red, the orange or red, I'm a little colorblind, so I can never quite tell, is the eddy inactive years. And what you can see is you see an effect, a shift in that entire distribution associated with the ocean eddy active years, which doesn't appear in the low resolution forecast. Okay, let's jump 1 minute. So I'm going to have to really skip way ahead here. Looking in the Atlantic, same idea. We have variability that's basically absent in the low resolution model, and a downstream effect from the Atlantic. This is looking at the SST and the 200 millibar heights and the geopotential height anomalies. It's not perfect, but you can see this the Gulf Stream is driving something just like Chris showed. And in fact, that leads to a very different 2-meter temperature anomalies. The upstream effect, I don't have time to cover this, but it's really nice results that's sort of hot off the press, showing you both how variability in the Southeast US has improved with the high resolution model, and but also the teleconnections associated with that. So this is looking at how that this is a low pass rainfall over the Southeast US, how that's correlated with the global oceans. And what you see is the models overemphasize the wintertime correlation. That's why you see that big ENSO signal, whereas the cross CMIP5 models and the low resolution model. But when you look at the high resolution models, they actually emphasize the summertime correlation, which is more related to the Gulf Stream and shifts in the Nash, and that's what's happening in OBS. And this is this shift in the Nash argument, and if I had more time, I could chat about that. But anyways, I'll finish up here. There is a reduction in the bias, but it's definitely not a panacea. We wish we could generate these long simulations with the high resolution model so rapidly, so we could exercise some of the tuning that we've always done with this more modest resolution version. So there's a lot of work that needs to be done. There's hints that signal to noise paradox is reduced in the high resolution model. We're still testing that, but we do think we have some pretty compelling results that we're going to report there. And then the real point I'm seeing is that the local imprint of some of the large scale processes is definitely different in these eddy resolving, if you will, simulations. And there's a downstream and upstream effect where people live. And I'll stop there.
Great. Thanks, Ben. We have a few minutes for questions. Feel free to put them in the chat or raise your hand. And while we wait, I do have a quick question, Ben. Sure. So some of the metrics that you used to evaluate early on in some of the earlier slides were based on ocean heat content and looking at deeper levels. And I was wondering what the differences were perhaps in some of those deeper levels when you increase the horizontal resolution. So what happens, in lower levels?
So I think the two figures you're referring to, let me get them up here. So this is looking at the local SST and the heat content from 700 to 1,000 meters. When you look at the upper 400 meters or 300 meters, certainly the lower resolution model lights up more than it does here, and as does the high resolution model. So the biggest difference is basically below 500 meters. That's where the higher resolution model is really lighting up compared to the low resolution model. And like I said, we think I emphasize think, it's because these eddies have a huge barotropic component. So there's a lot more vertical communication that penetrates all the way down to well down to 1,000 meters. When you look at this is the turbulent heat flux, same kind of story here. I'm looking at the upper ocean, but the same kind of story. If I went deeper, the correlation would go down quite a bit in the low resolution model in panel B, and in the high resolution model, it would also go down, but not really as much. And those eddy-rich regions still light up.
Great, thank you. And we have a question in the chat from Doug Smith. Great talk, Ben. You showed lots of ocean impacts of the high-res ocean, but do you see clear impacts on atmospheric circulation?
So yeah, I kind of raced through that, Doug, because of time. And so I just thank you for asking. I appreciate it. Were you a plant? So if I want to, what I'm showing you here in this picture is essentially a composite of times when the observed SST in the top panel and one labeled B, the observed SST and the 200 millibar geopotential height anomalies. And so what you can see is, you see a focused circulation response due to the Gulf Stream anomalies. If you go to panel C, contours again are the geopotential height, you see that focused response and wave train downstream associated with Gulf Stream being warm, but you don't really see that in the low resolution model. It just doesn't do that. In fact, it overemphasizes sort of an ENSO-like response, and this doesn't quite get it. The key figure here is the 2-meter temperature anomaly. So if you look at the 2-meter temperature anomalies associated with that warm Gulf Stream and whatever the low resolution model is doing, they're totally different. So these are showing you the 2-meter temperature anomalies associated with that. So yes, we are seeing a big response in the atmosphere.
Great, thank you. And if you have any more questions for Ben, please feel to put them in the chat. Ben, if you're sticking around, you can interact that way. Our next speaker is Isla Simpson from NCAR. So Isla, if you can share screen. Again, you can place questions in the chat as well during Isla's talk, and we can answer them afterwards, or raise your hand after Isla is done speaking. Isla, I'll give you a 2-minute warning.
Okay, thanks. Does this look fine?
Yes.
Okay, great. So thanks for the opportunity to speak in this workshop. So I'm going to talk about biases and variability in the North Atlantic and what that might mean for our ability to predict the region. And so this work is a couple of years old now, so I apologize to those of you who've seen it before, but it's, I think, relevant to the topic of the workshop. So there have been a number of studies that have argued that our global climate models, they tend to underestimate multi-decadal variability in the North Atlantic jet stream. And so each of these studies argued that by looking at the wintertime average NAO. And I'm going to make the same argument here, just with a slightly different metric, a more general metric. So I'm just going to take 700 hectopascal zonal wind over this North Atlantic domain. And at each grid point, take the time series for a given month or a given seasonal average. So if we're looking at January, just string all the Januaries together in the record, and then calculate the 20-year running mean of that time series, and then calculate its standard deviation. So that just gives a measure at each grid point of the variability in the zonal wind on kind of 20-year timescales. And so this is what that metric looks like for ERA 20C reanalysis, which is going to be our observational product. And I will argue in a minute that we can't trust this. And this is for the wintertime average from December to March. And then this is what it looks like in the CSM1 large ensemble. So this is a 40-member ensemble of coupled historical simulations. And then this is the difference between them. And then the gray here is showing regions where the observed or reanalysis variability lies within the distribution of the 40 members of the large ensemble. So what you see in the yellow here is that there's more low frequency variability in the real world than what you get in any of the members of the large ensemble. And if we look at that for the individual winter months, we see a pretty strong seasonality, and then there's more variability in the winds as you get toward the late winter. And it really maximizes in March. So I'm just taking an average in this box here, and rather than looking at the monthly values, just taking the 31-day running means over the course of the year using daily data. So we can see the full seasonal cycle of this low frequency variability. And you can see it growing over the winter, maximizing in March, and then dropping way back down as you go into April. And then here's all the other reanalyses. And so you can see that when they overlap, there's pretty good agreement between them. And you can see the low frequency variability in the jet stream in each of them. This is the same metric for the CSM1 large ensemble, and then the difference between them. And so they're particularly in the late winter, March, to a lesser extent February, and even lesser extent January, there's just more low frequency variability in the real world than what we capture in any of the 40 members of the CSM1 large ensemble. And it turns out that this is an issue that is there in pretty much every other model. So here I'm showing that same metric. This is the standard deviation of 20-year running means of zonal wind for March. And all of the red points here are the coupled historical simulations for CMIP5 and CMIP6. And the black lines are two observation-based estimates from 20th century reanalyses. And so none of the individual members in the whole of the CMIP5 or CMIP6 archive show as much low frequency variability as what we've seen in the observations. There's a couple maybe that come a bit closer in CMIP6, but the observations are definitely outside of our modeled distribution. We can look at how this discrepancy kind of varies as a function of the timescale that we're looking at. So this is again averaged over this box in the North Atlantic. And here we're going from just interannual variability of March averages on the left to 40-year running means on the right. These are two observation-based estimates, and then this is all of our 40 members from the CSM1 large ensemble. So what you see is on the high frequencies, the observations lie within the distribution of the large ensemble. It's hard to say that there's anything wrong on the interannual variability, but when you get out to decadal, to kind of multi-decadal timescales, you see that there's really much more low frequency variability in the real world. So I just want to show what the implications of this variability are and why we should care about it. So if we just take two 31-year periods here, the 31-year period centered on 1995, and then the period centered on 1950. And you see that in March, there's really a drastic difference in the structure of the jet stream between these two 31-year periods. And that has implications for precipitation. So in the later decades, when the jet stream was strongly tilted, Scotland has a far higher precipitation climatology than the Iberian Peninsula. But if you went back to the period centered on 1950, the precipitation climatology is pretty different. And Scotland and the Iberian Peninsula have pretty similar precipitation climatology. So this matters for the weather and climate of Western Europe. And I'm not going to show this here, but we argued in this paper that you can kind of use these precipitation observations as an independent verification of the magnitude of the low frequency variability in the jet stream. So I think we can really trust that this happened in the real world. So what caused this variability? So one thing you could question is this just sampling of higher frequency noise, maybe not really any underlying cause of the low frequency variability. And so I'm just going back to the metric I showed at the beginning here, the standard deviation of 20-year running means. And then here in gray, I'm just showing regions where the magnitude of that low frequency variability is not larger than what you'd expect from just sampling year to year white noise variability. And what you see is that the model is completely indistinguishable from white noise. There's no real low frequency variability to speak of in the jet stream in the model. You can just randomly sample marches, string them together, and the magnitude of the low frequency variability that you see is kind of consistent with that. In the observations, that's also true kind of over the ocean in the early winter, but in March, when the very low frequency variability maximizes, that's not true. And it's also not true in the wintertime average. And so the chances of obtaining this magnitude of low frequency variability from just the sampling of white noise is really small. And if you even accounting for the fact that you've done multiple tests here, it's really unlikely that you would just get this by chance without there being some kind of underlying cause of the low frequency variability. And if we go to the CMIP5 and CMIP6 models, and in gray here, I'm just showing the range that you'd expect for the low frequency variability if all there was white noise and you were just sampling that. And all of the models are really consistent with that. This is assuming the standard deviation of the observations. But there's really no kind of low frequency variability to care about in the models in the jet stream. But in the real world, that doesn't seem to be the case. And so we can kind of be motivated to try and understand what's going on in the real world. And an obvious thing to look for is whether there's a connection with sea surface temperature variability. And so if we take our winds here in the North Atlantic box in March and calculate the 20-year running mean and then correlate that with sea surface temperatures globally, this is the pattern that you get. And when we're looking at 20-year means on a kind of 120 or so year record, we really have very few degrees of freedom, maybe 5 degrees of freedom. But the significance test that we're using here is trying to account for that. And there are still some regions that do pass the significance test. So in particular, the variability in the jet stream is strongly negatively correlated with sea surface temperature variability in the subpolar gyre region of the North Atlantic. And this pattern here kind of looks like what you pick up with traditional indices of the AMV on these timescales. And indeed, if we look at the Trembreath and Shea index of the AMV, and we look at the correlation between the winds in the North Atlantic and the AMV, you can see that we have a correlation of about -0.9 in March, which does pass our significance tests, albeit marginally, because we just have so few degrees of freedom. And if we extend the data record back as far as we can really go with the 20th century reanalysis back to 1854, that picture holds. But again, it's very marginal because we're looking at low frequency variability on a short record. And so here I'm just putting up the time series going back to 1850. On the left is unfiltered, on the right is 20-year running means. Black is -1 times AMV, and red is the winds in this North Atlantic box. And so on the high frequencies, there's all sorts of noise there, they're not coming along together. But even without filtering, I think you can see that kind of on the low frequencies, these two things are coming along together, and that becomes clearer when you look at the 20-year running means. And again, very few degrees of freedom, but these do pass our significance tests. But it'll be nice to see how this evolves as we go into the future to have more confidence. So at least from this correlation analysis alone, we might suspect that maybe sea surface temperature variability in the form of the AMV has the potential to be a driver of that low frequency variability in the jet stream that we've seen. And we know that our coupled models, they tend to underestimate the AMV. They don't have the right amplitude of low frequency SST variability. So we could ask, does this variability in the jet stream improve if we prescribe the observed historical sea surface temperatures? And so if we go back to our CMIP5 model plot here, and then in black, I'm adding on 2 10-member ensembles with prescribed observed sea surface temperatures, one from CSM and one from the ECMWF model. And these just look like the coupled runs. They sit within the range expected for white noise, and they don't come close to the magnitude of low frequency variability we've seen in the real world. So even if you give the model the right SSTs, it doesn't produce the low frequency variability in the jet stream. So if we did want to argue for SSTs forcing the jet stream, then the models would have to be deficient in their representation of that response to the SST variability. But of course, all I've shown you at this point is the correlation between the SSTs and the jet stream, which doesn't tell us about causality. So how can we convince ourselves that that correlation represents an influence of the SSTs on the jet stream rather than the other way around? And we can convince ourselves at least that it's not the other way around by looking at the decadal prediction large ensemble that Steve introduced yesterday. So this is initialized decadal predictions where the ocean and the sea ice are initialized from observation-based states. And those states are derived from a forced ocean and sea ice simulation where the ocean and the sea ice models are run with observed surface fluxes. And so from every November of the simulation, those ocean and sea ice states are taken and combined with random atmosphere and land states from an uninitialized large ensemble, and then evolve for the next decade under historical external forcings. And so this here is showing the prediction of sea surface temperatures in the subpolar gyre region of the North Atlantic, where we had seen this connection between the SSTs and the jet stream. And this is at 10-year lead time. So the black is the observed SSTs, and the red is the decadal prediction ensemble mean at 10-year lead time. And again, we really don't have very many degrees of freedom. We basically have one wiggle here, but the model is capable of predicting this one wiggle at 10-year lead time. So the model predicts the SSTs, and it's not just persistence, right? It starts somewhere here, and over the next 10 years, it knows it's going to go positive. In contrast, if we look at the prediction for the winds in the North Atlantic, the model does not predict the winds. So this is at 5-year lead time, but the same is true at shorter and longer lead times. So what this tells us is the model is predicting the SST variability without predicting the winds. So it's not simply an SST influence on the ocean mix layer that explains the connection between those two. Rather, there's a role for the ocean circulation, and the initial states that are used in this DPLE are providing the information that is allowing the SSTs to evolve over the coming decade. And when you look at the uninitialized simulation, so only the influence of external forcing, that does not produce the low frequency variability. So just to summarize what the DPLE tells us, well, first of all, it's a coupled case where we have realistic amplitude SST variability without realistic variability in the winds. So it's more evidence that if you give the model the right SST variability, it doesn't capture the low frequency variability in the winds. But perhaps more importantly, the initialized model can predict the SST variability at 10-year lead time without predicting the winds in the short term. So this SST variability is not simply a result of the direct influence of the winds on the ocean mix layer. There's a role for the ocean circulation, and the initialization is giving us that information. And I won't go into the details, but Steve has a paper that describes where this predictability is coming from in the ocean. So in terms of the causality, at least the correlation does not represent an influence of the winds on the SSTs directly. So there's no real reason to expect those two things to be so correlated without a lead, unless the SSTs are influencing the winds. So it's a bit of an indirect justification. Whether the SST variability is forced or internal, I think is still an open question. We argued it was internal, but it could be forced. But either way, I don't think it changes the interpretation that we would argue that the atmosphere is not responding correctly to the SST variability. It's hard to explain the DPLE in any other way. If external forcings were forcing the SSTs and the winds separately, it's hard to reconcile that with the DPLE, because the decadal predictions know where the SSTs are going to go 10 years ago before the winds kind of would go there. So the hypothesis then is that there's this low frequency variability in the late winter jet stream that is being forced by sea surface temperature variability. It's due to variability in the ocean circulation. And of course, there could be a role for the winds in driving that, but it's the winds further back in time, not these kind of instantaneous March winds that seem to be correlated with the SSTs. And this is in agreement with some other observational studies that have argued this in the wintertime average. But we've argued that this seems to be a much bigger connection in the late winter, but we don't really know why at this point. And we'd argue that models may not be responding correctly to this low frequency SST variability, which I think is very aligned with what we heard from Doug and others today. And so this is concerning for our ability to get decadal predictions, but I'm slightly more concerned about our ability to just predict the overall climate change response. So if you look at sea surface temperatures that are associated with the AMV, and then this is just a figure of SSTs by the end of the century from one of the IPCC reports. And so there are a lot of similarities, although with the sign flip, but you have the warming hole in the North Atlantic, the kind of horseshoe pattern in the climate change response. And I think we have to question whether we're really going to capture the atmospheric circulation response to these SST anomalies correctly. So what can we try and do about it? Well, we can try and understand the mechanisms and what's going wrong. And that is difficult because no model seems to be producing this kind of low frequency variability that's coupled to the SSTs. We could try to get it in a model. And I think the easiest thing to try is to increase resolution. These are some results from the Primavera simulations, which have varying resolutions. And these are shorter runs, and they're run with observed SSTs. And so here I'm just showing the difference between two 15-year periods where the difference in the jet stream was large in the observations to see whether these higher resolution models are coming closer to producing that difference. So these are our CSM simulations. And then this is going from high resolution on the left to low resolution on the right. And the black line is the observed difference. And so there's no indication that going down to a quarter degree really necessarily improves anything in terms of this low frequency variability. But maybe we need to get higher resolution. Okay. Higher than a quarter degree. And I think there's some evidence that maybe things would change. This is from a paper by Adam Scaife and others. This is showing the eddy vorticity forcing of the NAO and the upper level geopotential height anomalies associated with the NAO. And so maybe there's some indication, these are different, I think, Met Office resolution models, that maybe when you go to higher than quarter degree, maybe something would change. And so one of the things we want to do in the coming months with CSM is to run one long AMIP simulation from 1950 to 2020 with regional refinement down to 1/10th degree in the North Atlantic, 1/8th degree, and take SSTs from a 1/10th degree forest ocean and sea ice simulation so we can capture the eddies like Ben was talking about, and really just try and push the limits of our resolution to see whether anything changes about the nature of North Atlantic jet stream variability. So here's my conclusions. Models seem to underestimate low frequency variability in the jet stream, and we've argued that this is related to them not accurately capturing the atmospheric response to SST anomalies. And I think this is probably also related to the signal to noise paradox issue and this general idea that models are not responsive enough to lower frequency predictable boundary conditions. And if the models could be improved, we have potential source of predictability in the North Atlantic. If we can't do that, we could also try and bypass this issue by looking at what is predictable, like the SSTs, and then using the observed relationship with the SSTs. If we have a longer observational record, that's going to improve our confidence in this connection. And I think it's worth seeing whether pushing the limit of model resolution improves this. So that's all I have. Happy to take any questions.
Wonderful. Thanks, Isla. So raise your hand if you have a question or put it in the chat. And we do already have a question for you, Isla, in the chat from John Dunn. So while the seasonal evolution of the northern about 50-degree north latitude peak seems relatively smooth, the separate southern about 30 degrees north peak emerges suddenly in February through March. Do you understand why?
No. Let me go back to, so it's, you're talking, yeah, I'm not sure I'm totally seeing, it's more, you see it kind of arguing that February, the southern lobe has not increased as much as the northern one. Yeah, I have not, I don't know why that is or whether that's really a robust thing. I could look into it more though. I hope I've picked out what you were looking at.
Yeah, I was just looking at that the upper right panel where the southern peak just is very red suddenly.
Yeah. Yeah, that's true. Yeah, I had not really noticed that.
Great. Any more questions? And while we wait, I have a question, Isla. I was curious about whether you've taken a look at this over, let's say, the North Pacific Basin. And yeah, just what was some of the motivation for North Atlantic? Is it AMV or?
Yeah, so I have not really looked in the North Pacific just because when there's much less agreement among the two 20th century reanalyses in that region on low frequencies. They differ quite a lot, whereas they really agree in the Atlantic. So I really focused on the Atlantic just because we knew what had really happened in the real world. But yeah, people always ask that, and I never look into it, but I should look more. But I think it's a little more challenging to know for sure what the real world did in the Pacific.
Okay, and we have a question from Doug Smith.
Thanks, Isla, for a fantastic talk. So I just wanted to question you about this causality issue between the SSTs forcing the winds, because in my analysis, I found that when you selected the ensemble members with the correct NAO, then that gave a much better prediction of the SST pattern, the AMV pattern. So my conclusion from that was that the SSTs or the AMV pattern is not the sole driver, at least, of the NAO signal. So I wondered whether you'd looked in other decadal prediction systems as well as the DPLE to see, if your conclusions are robust across different systems.
Yeah, I have not. I've only looked at the DPLE. So yeah, it's definitely hard to reconcile that view with the DPLE. But yeah, if that's not robust across other systems, I guess that would be important to know. There is like a little bit of a difference between in the structure of the SSTs associated with the AMV, depending on the time scale that you're looking at. And so it's really on the 20-year timescales when it's very focused in that subpolar gyre region, as opposed to kind of the whole horseshoe shape, is kind of where the SSTs that I am arguing is important. And I think on the higher frequencies, when you just get that kind of tripole structure, then it is the winds influencing the ocean. So I wonder if maybe both views make sense when you're thinking about different timescales. But yeah, we should probably try and reconcile that then if there's.
Yeah. Thanks.
Yeah. Okay.
Thank you. And we're going to switch gears now for breakout rooms. Thanks again, Ben and Isla. Gokhan?
Yeah, just everybody can stay in this main room for the time being. Todd will soon be putting everybody into their assigned breakout groups. And that'll start in a few minutes. The exceptions, the folks who are not who don't have an assigned breakout group are the program managers, and they have been all made co-hosts. And with that privilege, they can essentially follow the instructions that was included in my emails, starting on Wednesday, Friday, and also a reminder email on Wednesday. So if you go to the bottom of that email, you'll see the instructions for program managers to hop from one breakout group to another one. And if you need any help, you can probably send an email to Todd, and he'll be happy to help you after he sends people to the breakout groups. And as I said yesterday, the goal is essentially try to sort of come up with one or two topics that can be taken up by the modeling centers, and they'll be further discussed tomorrow. And if you can also come up or assign or choose a rapporteur for your working group, that person is going to be presenting tomorrow for about 5 minutes or even less. And then, so that's sort of the thing. And then we have about an hour and 8 minutes or so. And then the discussions, I mean, if possible, and if there's discussion, enough energy left in people, they can continue till 3:30 Eastern Daylight Time, 1:30 Mountain, and 12:30 Pacific Time. And we are not coming back to the plenary afterwards. So after the breakout groups end today, we'll resume again at 11 o'clock tomorrow. So go ahead, Todd. Hopefully this will work.
Okay, I'm going to send people now, and I'm going to remain in the main room. So if anyone wants to come back and needs help, you can always come back to the main room.
And I suggest also in the discussions, people turn on their computer or videos. I'm not sure whether I'm in the right group or not, Todd.
You could automatically join any room.
Okay. So this is, which one is this one that I'm in right now?
You're in the main room. So you press the breakout rooms button. You'll see
Right,
the rooms.
Clara Orby still is in the main room. She should be the lead for one of the breakouts.
Yeah, I think it was trying to transition me over, but it just kicked me out of the meeting. Could you please try again? Thanks.
Yeah, I'll put you over there, yeah? Okay.
Okay. So these 6 people are in the main room right now? Is that the only?
Yes.
And all I have to do is just click on the breakout room number?
Yes, there'll be a join button.
Thank you, Todd.
Mm-hmm.